very technical to a deeper level. And that's what we have is we have a lot of very talented people here. We're going to start with my friend Lucas, which is a amazing teacher and also a mathematical and I also want to introduce you guys to Eduardo, which is an amazing guy. I also do these very good important
say like thanks for everyone coming here. It's like we go many things and people were like, sure, and so it's like very cool, very interesting, and amazing to see how as well. And yeah, thanks to our sponsors, thanks to Kaiser, that is not here, thanks to Florida, thanks to Netherlands Security, downtown, Oslo, thanks to our Paloma, and
very grateful this is going on and happy you guys came. Thank you so much, brother. And very important to say thank you to the Founder House for hosting us and always allowing these amazing experiences. Thanks, Nima. Thanks, Paloma. Thanks, team. Guy, Camila. Eric is not here today. Thanks, Fernando. What is your name? Thanks, Natalia. So, guys, we're going to start with Lucas Oliveira. What are we going to be talking about today, buddy? Yeah, so formal unification 101. I'm just going to ask you to speak a little bit louder because we are close here. There's no need for a mic. There's no need for electronic voices. And I think we can take this out.
I have one. But oh, okay, perfect. Okay.
Sure. Thank you so much, guys.
Okay. This is your computer?
No.
No. One moment. I need one. Pode tocar aqui, não tem problema? Oh. Me empresta o plugzinho desse cara aqui. Valeu.
Who has not tried Brazilian barbecue? Has anyone not tried picanha yet? You? Have you tried?
Yeah.
Yeah? Everybody knows?
First thing it is, yeah.
I don't want to get anyone too excited, but that's what we're going to be doing in about 2 hours. So today's
Nice.
Today's is Anita's barbecue guide.
Wow.
This is like the Brazilian pop star. So we got a pop star barbecue chef to get you guys the best picanha in Brazil.
Nice.
No pressure. Você é o melhor churrasqueiro do Brasil.
Funciona? Clica aí. Yeah, nice. Perfect. Start? Pode começar, tá gravando? Good afternoon. Guys, it's a pleasure. More? Yeah. Perfect. Guys, good afternoon. It's a pleasure to stay here to talk about some interesting things. And we have one bug. Perfect. The right way. Very nice. Today I will talk about some big numbers. Yeah. This is a total of the money lost in crypto since 2015. And in this last year, we lost $2.2 billion in some hacks. Yeah, this is a big problem. And the idea for this talk is introduce guys that don't know about formal verification to a new way, new approach, new paradigm for avoid this type of problem, this big problem, okay? And in 2025, we have 2.17 billions stolen. And we have a new problem that is physical violence and coerce against crypto holders. And we have a growth of 23% in personal wallets, yeah, stolen. And we have a big hack in this year. That's 1.3 billions of Bybits. And in this case, my friend Alexandre like a lot about privacy can solve this part. I don't know. Okay, this is a graph. We have a lot of hacks, and the trend is increasing the next year. Okay, but why? Today I will explain some things. My name is Lucas Oliveira. I'm a mathematician and cryptography engineer. I really love build libraries. Yeah, I understand something about cryptography. I'm a mathematician, but I don't know build something like this. But I really love build libraries. Yeah, and get these great things in cryptography and deliver for common developers is my love. I work with several great partners in Brazil, like Drex. I work a lot in Drex with Visa, XP, ClearSale, that today is Serasa, TechBan, and I am ambassador of Stellar. And with some great guys here, Felipe and Alexandre, I build one Floripo Web3. It's a different type of event. It's one event for onboarding Web2 developers to Web3. It's more for beginners, yeah, for understand the new paradigm of, okay, in Web3 you can be a nomad, yeah, you work with great things, money, decentralized. It's a different type, but have the same best guys, yeah. The idea in this lecture is talk about tests, something about mathematics, the market of the formal verification, tools, research, and yes, in the final we will have one proof, okay? How the software development life cycle works today in Web3. First, we build something, a protocol, a DeFi, and smart contracts, and then we test. This is the main idea. We test using TDD, BDD, fuzzy, whatever techniques or methodology for validate that what you write is right. Yeah, I think one idea, I write some code, and I expect that this code works like I think. Perfect. Then we submit this code to auditing, private auditings or published auditings like Arena, Code for Arena, Immunified, etc. And we get this report and fix codes, yeah, and then submit to production, okay, for interaction with user. But in the really, what happened is we receive a lot of attacks because in Web3 we have permissionless platforms, yeah. Anyone can connect with your smart contracts and interact with them. And then we are stolen.
TDD is test driven development, I think. TDD.
Yes. Test drive developer, and BDD is behave drive developer. Okay. Yeah. Okay. The wrong idea is think about more testings, yeah, because we have fuzzy. Fuzzy is a great tool and deliver a high level of assurance of your code, for testing your code. But more testings don't validate that your code is okay, yeah. The approach needs move for proofs and not testing. The idea is very simple. Think about your code. This part is very technical, okay? Think about your code. Your code starts here with an initial state and has some states. Yeah, some good states. Okay, I have users. This user is active or not. I have balance. This balance is 0 or not, and etc. And then we write more code and put more features in more states and some bugs, okay? And put more code, more features, and etc. And what happened? When I test my code, I think like this. I start here and connect, okay, the user will input this amount for this address, and then the contract will process in this way, and etc. and etc. And I build one path, yeah, a good path or bad path for testing my application. But I build another way, another path, and this another path I get one bug, okay? But the problem is, for you find all path that validate that your code works fine, you need make like an infinite possibilities for test your code. And this is a concept of correctness. Correctness is a algorithm concept, is a basic concept in computing that say, okay, you can validate in all cases that your code work fine. And the idea for build verification, formal verification, is make something like this. How? It's pretty simple. Think with me. We have one Solidity code, okay? It's pretty simple, but has one bug. It's overflow bug, because user have some balance and we don't check what's the balance, how much balance the user has, and add some bonus, okay? The traditional approach is using fuzzy to test 256 times case handle, input several different values for validate that this contract works fine, okay? But you are limited for these paths. You get it? You have 200 paths, 1,000 paths. Don't worry. You have these paths that validate if bug exists in this path, I will find. But if bug don't exist in this path, I don't find this bug. This is a problem. But I think that all guys here is engineers and less mathematicians. And today we don't really want to write mathematician proofs for each piece of code that we run. We want say hello hello ChatGPT, build on secure code for me. Yeah, this is we really want. And I bring one tools. We have several tools. I bring one tools for show. Okay, for show. Okay, I will say to one machine, hey machine, get my code, my test code, something like this, and write a mathematical proof, mathematical equation. And with this mathematical equation, I will prove that my test validates all possible cases. And this is almost, yeah? Is the pretty similar code, yeah? But almost gets these tests, it's the same test, okay? Almost is a tool, get this test and convert this test to a constraints mathematics. Mathematics constraints and build one equation logic. And then we submit this equation logic to STM solver. STM solver is like a machine that solves mathematics problems, okay? It's pretty simple. And this mathematical machine return for us, okay, this specific code don't have bugs or have bugs in this case. Yeah? This is a great idea behind of formal verification.
Look, what you were just describing, is it property-based testing, or you were actually proving a theorem?
Yeah. No. This is a proven approach. Yeah.
It's something like he's describing the properties and extracting like
Yeah.
the constraints for it to find the proof.
Yeah.
I guess.
Yes. Perfect. But the
The thing is that C3 is only, it's SMT. So you have satisfiability model, a few decidable theorems. A few decidable theories. So you're kind of constrained to a certain degree to what you can prove with that.
Yeah. But the thing is, almost build these constraints, this logic mathematics for us.
Okay.
We can write in manual, and we have another tools like Sartora Proof Verifier. That's another language that we can write a constraints for our test. But I want to bring this because it's more simple. And the market today is this size. We have several protocols using this approach because it's more secure, but more secure is a very strong way to describe, but we can validate more cases in with the less time, yeah? It's more quickly. We have Stellar, SUI, Curve, Uniswap, yeah? Cosmos, SDK, verify the protocol based using formal verification. And I bring some tools, yeah, that you're using today. And I bring Slither. Slither is a different tool. Is on static analyzer, yeah, for Solidity code. But this is insightful for you. Formal verification is a piece of the SDLC for you putting in the top, okay? If your code has bugs, common bugs, you not will solve your simple bugs with formal verification. It's not, don't work with this. The idea is use Slither because Slither is a pretty amazing tool, yeah, for validate. Okay, my contract don't have simple bugs. Yeah, my contract is secure, and then you use fuzzy tests with Foundry or another tool, and then you put formal verification for okay. In this case, in this way, my codes don't have any type of bugs. Yeah, we have Certor Approve. That's another tool. STM Checker, but it's Solidity between. We have Almost, that's growing fast in these last years. Control, that's another tool. And Meteor. Meteor is more legacy. And we have Picos. Picos are tools for ZK circuits. I have one idea. It's an unpopular idea. That ZK cryptography and Web3 in general is not very secure because we have we don't have a lot of programmers and cryptographers enough for validating all parts of things that works in today. Yeah, and because this, I really grateful for Alexandre. Applause for Alexandre.
One more? Yeah. One more? Yeah. So I know that Solidity has built-in SMT checker, and people usually turn that off for gas savings, because I think automatically it's going to convert that to byte order somewhere in the beginning in the approach. They add verification to the code, right? So if I have a built-in, so the SMT checker is not for exactly for formal verification, right? It's kind of a compiler.
Yeah.
Thing, right?
Yeah. It's like a Slither and Fuzzy is a more one approach for you validator.
Because I know that the SMT checker is built into the compiler, in the Solidity compiler, right? So whenever you write any sort of Solidity code, you're going to optimize. You're not using you, you're not doing straight assembly. It's going to add steps to the verification. And I know someone knows this very well here. Can someone help me with the SMT checker? Drew, maybe Felipe. So do you know a little bit about the SMT checker? Because I know.
No, I'm not that.
Keep on.
Okay. I'm very grateful for this initiative because we need more cryptographers, yeah, more developers with high skills in security because we have $14 billion stolen, yeah. And for finish my lecture, I have one proof for you, okay, for validating that you really understand the talk, and we will starting here. Get your phone, scan this. Oh, sorry, I need to share. Okay. Okay. Yeah, it's efficient. This is a game for testing that you understand the lecture. What? Okay.
Where's my money?
Yeah. Send money. Approve this contract for me. Approve this contract. Tem um volume da TV? Aumenta um pouquinho, eu acho que tem um som. Tá saindo só no meu... Ah, peraí. Aumenta um pouco mais. Tá saindo, mas tá bem baixo. Tá, peraí. Deixa eu ver se é aqui. Here. Perfect. Yeah. All ready? Okay? Come on. Perfect. Response quickly, okay? Very quickly. How much was stolen in cryptocurrency in 2024? 22 bitcoins? 220 millions? Come on, come on. Oh, it's 2.2 millions. 5, 4, 3, 2, 1. Woo! Oh, yeah, congrats, guys. Oh, what? Who is? Woo! Perfect. More quickly, more quickly. What was the biggest individual hacks in the history of the cryptocurrency? Mentioned in these presentations. MTGOX, CoinCheck, Bybit, Running Networks. What? Oh my God. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, so wrong. Yeah, a Bybit. Okay. We need 40 points. Come on. What is the correct sense for Web3 SDL? Test, building, audit prod, auditing, build, test prod, building prod, test, auditing, or building, test, auditing prod? What's the correct path? 5, 4, 3, 2, 1. Oh, yeah. It's building, testing, auditing, in prod. And install it. Woo! The last one. How does formal verification ensure code correctness? Subject to manual review by experts, perform millions of tests, use artificial intelligence, or use mathematician proofs? Come on. 5, 4, 3, 1. Okay. My baby's crying. Come on. Come on. Woo! Woo! Where? Who? Woo! Perfect. Okay.
What does she get?
Okay. I for more one thing for finish. Oh, yeah. I built one NFT for this lecture. Yeah. And if you want this beautiful NFT, connect with me after. I will give you a pull up, okay? And it's a pleasure to stay here, talk some incredible things. I'm very grateful for Alexandre from the Haus and your guys that come to here to learn more crypto and build one Web3 more secure.
Yeah.
Pode.
Alex, about the SSD for Swift, they use for check requiring the answer.
Oh, okay, so.
Vai usar esse por aqui. Tem. O outro é o meu.
We should know that guy.
Very good. Very good.
Pode ser no cantinho direto.
Ele já vai o microfone, já vai o
Ah, entendi.
apresentador. Vamos direto. Ah, certo.
It's been a while since the last time I was so nervous for giving a talk. But the thing is that I don't know, among so many smart people that actually hands-on working on this stuff, it's a little bit overwhelming. So bear with me if I. Okay, so the idea here is to talk a little bit about a proof system called Lean and a formal framework built on top of it, which is called Clean. I'm not so sure if I nailed the right level of abstraction here, if I'm being too abstract or too low. So please correct me if something is not clear at some point, and I'll do my best to try and make it clear. Because there are some things here which are, a bit complicated, and I might not have the answer right on spot, but I'll try my best to do so. Okay? Who the hell am I? So I'm associate professor at Universidade Federal Fluminense, which is a university close in Rio. We usually say Rio, but it's Niterói, so a city nearby. And my background is on formal semantics of programming languages and formal verification, mostly using the mod system, which is an algebraic rewrite-based system. And I did some work on that. ZK4All is just an organization that I built, and nowadays it's just me and Samar working on it, and we are, doing some fun stuff using zero knowledge. In the past, let's say, 3 or 4 years, maybe, I started to work on zero knowledge stuff and looking at full homomorphic encryption as well. Faster or higher?
Higher.
Okay. And it's really cool stuff. So that's the reason why I put these slides together after kind invitation from Alexandre on that. Thank you, Alexandre, for giving me the opportunity. So we all know that testing is cool. Proving is also cool. And these are some of the, sentences that we may find on the web about the difference between testing and proving. I think from what if to it is one of my favorites, but also testing builds evidence and proofs. Build certainty is probably also very nice. Property-based testing is also very cool, but it's not proving. So, okay, so proving is cool. We know that perhaps from algebra in school. But how do we do this? How do we make it work? And the answer is obviously with logic, formal logic, mathematical logic, most speak. There are many approaches to do that. We can classify as first order or higher order. And the one I'm going to talk about here is a higher order one using type theory, which is the basis for Lim, for Koch. I don't know how many. I should have started asking this question before. How many of you have experience with Lean or Koch, proof assistance? My goodness, mostly all of you.
A bit.
Yeah, so I'll probably move faster then. So what I want to talk a little bit about is about type theory, which is the foundation for these two systems. So maybe we can start back with the Brouwer interpretation of intuitionistic mathematics, which led to intuitionistic logic, and is essentially to look at logic in a constructive way. So to do that, what he does is to reject the law of excluded middle. So this is nice if you're in a finite setting, but if you extrapolate that into infinite stuff, then it's not so cool. So this is the basic for this constructive approach to logic. Then Martin Luff proposed his intuitionistic type theory, and it's very cool because you can actually program in the logic. So you have constructions to reason, and you can program in this logic. Another element which is very important about in this soup of things is the Curry-Howard isomorphism. And the idea is essentially that you can see computation and deduction as two sides of the same coin. Okay? Everybody with me so far? Then Thierry Coquin, Gérard Huet, Frank Fanning, Christine Pauline Morin, together they defined this very nice thing called calculus of inductive constructions, which is, I think we have an enthusiast.
I was, yeah, exactly.
You're right.
Yeah.
And this is actually the basis for the foundation for two very important tools nowadays, which is Lean, one of them, and nowadays it's called ROC, but before it was called Koch. There are explanations for that. Koch is because of the calculus of constructions, the symbol of France, and ROC is now because of how is it called? Hokenko? Say it again? Hokenko, exactly. But I don't really know how much of that is actually an evolution of Koch, but I'm sure there are many cool things there as well. But the focus is on Lean. So, so Lean is this functional programming language, which is also proof assistant. And its beauty, as I said before, it's based on calculus of inductive constructions. And it's beautiful because everything is done in the same framework. So you describe your theorems, you describe your proofs, and everything is in the same framework. So you have this very small core of a trusted basic language, and everything else is built on top of that. So from the programming language perspective, which is one of the sides that I was just mentioning, it's pure programming language, which means that we do not have side effects. So it's really functional programming. It's strict, so it's not lazy, as opposed to Haskell, for instance. And it has support for dependent types, which is another name for all the philosophical stuff that I was just mentioning before. Every expression is a type, and Lean also supports the notion of parametric polymorphism. I'll give some examples in a moment for those who are not who are impaired about this. Functions of first class, which is something that is quite common in functional programming, I would say. There's the notion of abstract algebraic data types, which is something that, I don't know, Haskell has, and probably was a language that made it more popular, I think. Maybe not. So it has structures for product types. It has inductive types for some types and tagged union. And it supports also pattern matching on top of all these things. This is a very interesting thing because in order for Lean to be a proof assistant, we have recursive definitions to be defined structurally, which means that you have to do it on sort of an algebraic type, for instance. So everything is defined on top of using terms in this type. Otherwise, you have to provide a proof of termination of that function. If you're using, I don't know, well-founded
recursion.
Exactly. For effects, what we have are monads, which is also something, you know, I would say also common nowadays in functional programming languages. Examples of that are input and output, errors, the notion of managing state. All these things can be done with monads. So essentially, you have a kind of imperative flavor to something that otherwise is functional. So here are some examples, very simple ones, of course. The first one is a function that, given a list, it calculates the length of that list. And it's a polymorphic one, so you don't have to say that every element in this list has the integer or natural type, can be any type at all. And essentially, it's defined by pattern matching on the given list. And if it's empty, which is the meaning for this notation here, it returns 0. Otherwise, in any other case, it will be the concatenation. It's the case of the non-empty list, which is something concatenated with a list of T1 called T1, and we add 1 to the length of that. So it's a usual recursive definition. This is the syntax for defining inductive types. So in the case of option, which is also very a common thing nowadays in programming, I would say, either you have some value or you have none. So you have just two branches that together they comprise an inductive type. And a function get or default is a function, for instance, that either returns the value if there is some value there, or it returns none otherwise. Or, sorry, it returns a default value otherwise. So the function receives two arguments. One is the option, and the other is the default value. And depending on what's there, it returns one or the other. And the last one is just a an example of a simple I/O function that receives a monad for output, in this case, and simply prints hello world in the screen. Since everybody here knows Lean, I think this is probably very straightforward to you, but for those who are Lean impaired, is everything clear? Any questions so far? Cool. So, as I said, Lean is beautiful because not only Lean, other approaches using the calculus of inductive constructions are as well, but the thing is that everything is in the same framework. So we can define functions, we can define types, we can define theorems, and we can define proofs using tactics. So a tactic is essentially, for those who know some rewriting, it's pretty much like a strategy. So it's essentially a sequence of commands that you want to be executed in order to prove that a certain property holds in a system or in a theory. And the examples that we are going to see have many tactics being used. Some of them are simple simplification tactics like simp or RW for rewrite or cases. So simp, it essentially applies a certain number various rules and other proofs or other theorems that are marked as simp via some sort of annotation, okay, and its purpose is to simplify according to these theorems, okay, or other tactics. Rewrite simply takes a certain equality and applies it as a rewrite rule from left to right. And cases is simply case analysis. So we can split something into its different values. For instance, you can reason inductively using cases. The base case, for instance, is case 0, or the successor of some natural number as the second possibility. These are more powerful strategies. So ASOP, sorry if I'm spelling it incorrectly, but it's a strategy for automated reasoning. It performs search, rewriting, and application of rules. Green is a very powerful strategy that I'm going to show to you in an example, which is actually in the front page of Lean. So it will probably not surprise many of you, but it's a very powerful strategy that performance normalization, congruence closure, which is a decision procedure very common in verification, rewrite linear arithmetic, and omega is also a very powerful one for linear arithmetic using Pressburger arithmetic, which is a decidable arithmetic. It essentially doesn't have multiplication. Cool. So we have all this stuff. Why does it need to be formal? So we were talking about the need of proofs. We talked about one particular framework, but why do we need this framework? Why do we need all this stuff? Because all of you know that program verification and formal verification in general is not an easy thing to do. Why don't we just stick to the good and old pen and paper approach? Let me try to give you an example using what I was telling to you guys, that it's on the first page of the Lean language. It's a very nice example. So the idea is to, let's just take a look in the proof, in the natural deduction proof of the existence of a prime factor. So prime is defined as usual. So it's a number strictly larger than 1, and there can be no other number that divides n. Okay? So the theorem says that for each natural number, for every natural number, there exists a prime which is a divisor of n. Okay? This is a known mathematical fact, so to speak. So, okay, so written formally, it's like, I wish I could point it with the laser, but. So this is the same, what I just said in plain English. It's how we write it in mathematics. And the proof is essentially, once we take the hypothesis that the given number is larger than 1, then we split this in 2 cases. One case is when the given number is a prime, and then it's trivial because we can find the divisor. It's actually the given n because it's a prime number. And if n is not a prime number, then it's a composite, and we have to first apply the definition of what a composite is. Then we do some induction in smaller numbers, which essentially goes backwards, 1 by 1. And then with the induction on smaller numbers, we find this prime. And then by transitivity of divisibility, we find that this prime is a divisor of n. I see that you're making it, it's hard to keep up, right? It's kind of, sleepy right now. So this is precisely the point why we needed formal proofs. Because can anyone raise your hand and say this proof is not correct or this proof is correct? No. It's very hard to do that. And this is not a very complicated thing. So this is precisely the reason why we need formal proof. And this is done in Lean. What in the previous slides that took me like, I don't know, 3 slides or 4 to spell out the proof, which is a very nice spell out. The proof is correct. And the reason why it's correct, because it was, GPT gave me as a as an explanation for this proof here. So the prose is good. Yeah, go ahead.
You use these symbols in the language?
Yeah, yeah. Yeah, yeah. Yeah, exactly. So this is a classical proof, okay? Because as I was saying, the basis of Lean and Koch and other guys is type theory, and it's constructive. But there are ways of representing classical proofs as intuitionistic theories and theorems and etc. Yeah.
You don't need to recalculate the problem every time to have that done.
This is once and for all.
Yeah, okay.
So
I don't need to go every time and then
no,
everything.
no. This is correct, and that's it. You don't have to do it anymore. And you can see here all the steps that I explained to you before, and on each part here. This is actually part of a larger example, which is very nice in the front page of the Lean prover. Cool, but we are not here to talk about type theory and proving things with Lean. We want to do that in a cryptographic setting. So yes. So what we want to talk about is about zero knowledge proof circuits. So why can't we do this for those circuits? Because a zero knowledge proof circuit is just a program, and hence we can apply the same techniques that we use to prove to make program verification into circuits as well. Of course, there are a number of constraints, such as, we are talking about a finite field and a number of other stuff. And that's precisely where clean is going to present itself as a solution for this kind of reasoning. But before, let me say a little bit about what zero knowledge proofs are and what circuits are. So this notion of zero knowledge proof is probably due to Goldwasser, Micali, and Rakoff in their paper, which is linked here. If you get the PDF, all these blue label things, it's actually a link, so it's going to take you to the original paper. It's very nice to read, and it's actually a discussion on how to rethink the notion of complexity in NP decidability of NP problems. That's all where all this thing started. And it's a cryptographic concept, and the idea is that is everybody here familiar with zero knowledge proofs and circuits?
I know what is the concept, but I cannot explain it.
Yeah. So the idea is that the prover wants to prove that he knows a certain secret without disclosing it. So I'm the prover, you're the verifier. So I want to convince you that I do know something without showing to you the object itself. Okay? So very common example. I'm above 18 years old, so I'm you know, consider a formal. But I do not want to disclose my age. I do not want to tell you that I'm 55. Oops. And this is possible with zero knowledge proofs.
I heard an explanation that I can prove that I'm on our house without saying that, I don't know, I have two banners here, a pretty cool picture right behind you, a TV in the center.
Yeah.
It's kind of the idea.
So the idea is to have a proof about the computation that proves something without exposing the something.
Okay.
Right? So another example, which I think is very nice, I want to prove that I'm eligible for a loan without disclosing my portfolio.
Okay.
So there's the notion of credit score in US, I think in Brazil as well. I'm sorry, I don't know what this stuff, but I could prove that I have a certain score without disclosing I could prove that I'm eligible to a certain loan without disclosing my all the you know, my credit score and the portfolio. Okay, without giving all these details, right? And I give you the proof, you verify the proof, and that's it.
Awesome.
Cool. That's pretty much what I said. And zero knowledge proofs, they must satisfy the notions of completeness, soundness, and zero knowledge, which is also important. So in order to create these proofs, we have to write a circuit. And the circuit is going to give you the logic for the proof. So for what we want to compute based on certain inputs, produce a certain output, what is public, what is private, and how I can compose other circuits in order to construct the computation that I need to construct. Okay? Now this is precisely what I just said. So we have inputs, we have gates. So the analogy here is with hardware circuits. We have constraints, because as we are going to see, we do not have the notion of assignment in the usual imperative programming paradigm. What we have is the definition of a constraint. So we have the notion of certain variables, and those variables say that, I don't know, X must be larger than Y plus something. So it's not just, this is clearly a constraint, but when I'm going to show that, it's probably easier than trying to explain. But if you have an assignment, it's not an assignment. I'm not changing memory or anything. I'm just, you know, writing a constraint. Pretty much in SMT-like kind of thing. One such way of writing those circuits is using CIRCOM. It's probably the oldest language to write those circuits. And it's called the DSL for domain-specific language. So it's a language that was designed to write those circuits. And there's a, kind of long pipeline in order to produce a proof from a given circuit. So you have to produce there's a slide saying this, how the pipeline works. But the idea with CIRCOM is that everything is a circuit. And you have the notion of input, you have the notion of output, just like in any hardware-like logical circuit. You have internal signals. Every signal is a wire. So we can connect stuff using those signals. So when you put those two circuits together, we are going to connect them through those inputs and outputs and signals. As I said, it's probably here. Let's see. Yeah, I was saying that we don't have assignment. What we have is constraint construction. So the triple equals a constraint. The arrow to the left, it's like a wiring connection of signals. And if you have an arrow with simple lines, is witness assignment. So a witness, as you probably know from SMT or from SAT, is just something that given to a circuit, we can evaluate that circuit using that witness, and it must hold or not using that assignment. So I was here, a couple of examples here. So we are just saying that A times B equals C, which is a constraint. A plus B equals 7 is another constraint. We can have components, which is essentially an instantiation of a circuit. So what we are using here is defining a component called add that receives two inputs and outputs the sum of these two inputs. And the component that we are defining with this essentially is reusing it. It's behaving exactly as the addition would. So those templates, it's like is the containment for those constraints. So we define the template to create a circuit. And this template can be parameterized. So in this case here, we are adding not only just two numbers, but actually a vector of n numbers. Okay? And these are the things that we put together using the signals and the wires and everything. And this is what I was starting to explain before, but I thought it was best to leave it to this slide here. So how does it work? So we have a description of a circuit using CIRCOM, and then we transform that into another formalism called R1CS, which is rank 1 constraint system. Why rank 1? It's a property of matrices, which is the representation that R1CS systems use. It's actually quite complicated. The algorithms for generating proofs they are not a simple thing to grasp. R1CS is just one component of this pipeline. Then we need to perform witness generation. So we have to find an assignment that makes one particular circuit holds. So for this assignment here, which is found, generated, the circuit then will hold with it. That's the second step of the compilation flow. Then we actually generate a proof, which in the case of CIRCOM, well, it can generate other proofs as well, right? Or it's only is the case NARCs. the proof generated from CIRCOM is just only ZK snark, so it can be just ZK snarks, right? And the proof is zero knowledge, so it has the properties that I was just mentioning regarding not being able to identify the secret that the proof is carrying. It's succinct, meaning that the proof is small. It's non-interactive because when Mikali and other people started, the protocol for generating proofs was interactive. So it was necessary for the prover and the verifier to interact between themselves in order to generate the proof. But now with using Fiat-Shamir transformations, they can make this otherwise interactive proof into a non-interactive one. And that's it. That's every time we have a different witness, we have to generate the proof once again and go through this process once more. And that's the cost of that's the part of the protocol, the larger protocol, so to speak, that's really expensive, the generation of the proof. So the whole thing was devised to be fast on the verification. So it takes some time to generate a proof for certain under certain circumstances, but it's very, very fast to verify them. So that's the reason why usually we generate these proofs off chain, and then we have a verifier for them on chain. So it's common to generate a solidity code for the verifier of our circuits, and that's what goes on chain.
Can you, I don't know if that's maybe off topic, but can you comment on ZK snarks versus ZK snarks? Are those?
Yeah, there are different approaches. There are different techniques. ZK snarks or snarks, they have one step which is called
We can talk about that after too.
no, just slipped my mind, but just a moment. Ajuda aí, que o que tem no Snark que o Stark não tem. No, it's not pairing.
A diferença grande para mim é isso, de ser elíptica versus hash.
Não era isso que eu estava tentando. Não era isso que eu estava tentando lembrar, não. Tinha te respondo disso depois. O fato é que the fact is that he was asking about the difference between snarks and starks, and the fact that there is one part of the snark proof generation, which is very delicate, so to speak, that Stark does not have. The trusted setup, exactly. Exactly. So Starks do not have the trusted setup, and which is kind of Achilles heel of snarks, if you will. But the cost of that is that Starks generate a very large proofs. So one thing that some people do is to generate a snark proof from a Stark proof. So we have a very large Stark proof, but I have a very small snark proof that I have a Stark proof. Okay? Okay. So this is an example in CIRCOM. That's the example that I'm going to use. How about time? Should I move faster or? Thanks. Nice. But just a quick check here. Everybody with me? Is it too abstract, too concrete, too something? Okay? Okay.
Yeah, are these like circuits represented in graphical form somehow, or just like visually?
I'm not aware of, but maybe there are some tools to render the circuits graphically, but
Yeah,
usually
I don't know if it helps with the intuition anyway.
Well, if you have a very large system, a very large circuit, it's probably good. but for small ones, just the textual representation should be enough. So this is the E0 comparator in the circumlib, which is the example that I wanted to show you guys. And in circum, it's written like that. So essentially what it checks is that if the input in is either 0, 0, 1, and outputs a number 0, 1, depending on the fact that the number is 0 or not. So just have this in your mind. This is our running case here. Okay, so so far, let's a quick step back. So we started why proofs are important. We decided to choose one particular approach for proving, which is the high order one type based on type theory. We've seen one particular tool to prove in type theory, which is lean. Then we moved to the zero knowledge world. We saw some basic concepts about zero knowledge proofs and how to create them. And now what we want to do is to put these two worlds together. So we have lean and proving in type theory. We have on the other side, we have circuits, we have zero knowledge proofs, and we want to put them all together. And one way to do that, never mind guys, you're going to tell me you're wrong, it should be done in a different way. But I'm also not the author of Clean, so I'm here just to explain my experience, to share with you guys an experience that I have. So Clean is one such, yeah?
The other slide where you're showing code, that's lean code, right?
No, this is Circum.
Okay, so that's Circum, and then you're going to show the language later. That's how you're not lean, so that's embedded in lean. This is,
Yeah, I'm sorry about that, because this is actually, exactly. This is commented code in the Clean implementation of the is0 circuit. So if you follow that link, that's what you're going to see, but that link points to the comment. And below the comment, you have the implementation in Clean, which is essentially lean using certain data types from the programmer perspective, right below.
So you might show it later, but then, so Clean is implemented as a PSL inside.
Exactly.
Right?
Yeah.
And then do you use like tactics to do your parse?
Exactly.
So you do meta programming.
No, I mean, there's no tool, as far as I know, that goes from Circum directly to Clean. So what we have is that we have a manual translation, but we're going to see that it's, at least for the very simple ones, it's very straightforward to see the Circum implementation and the lean, the Clean version of it. Because a circuit in Clean is nothing but a function manipulating a monad. Spoiler alert. Because I'm going to say that in a few seconds. So Clean is this high-level domain-specific language. From the programmer perspective, it's just an extension, instantiation of certain data types, which are implemented in lean. Of course, there's a lot of things going under the hood to support all the proving that's necessary in order to make sure that a circuit is sound and complete. I'm not going to go into the details of that because, frankly, I don't know myself. It's a lot of stuff, complicated stuff back there. Well, I don't know because I never studied it, but it's not trivial. As I said, Clean uses a monad to represent a circuit, and it defines its own tactics to help in the proof process. So yeah, as I said, a circuit is a monad, and the notion of a monad, just anecdote, it's actually an abstraction from category theory that was borrowed from category theory by a guy called Eugène Maugy. And it's useful for programming with effects in a functional world. And after that, Haskell, for instance, reformulated its standard library completely in order to use those monads. Lean uses monads as well. And on top of that, the clean guys, they define their notion of circuit, which is essentially, as I said, a function that takes an offset, which is something I'm not going to mention to explain in detail right now, and a list of operations, which will hold eventually just the set of constraints that that circuit has, and it's going to be used in the process of verifying that that circuit is actually correct. Some details about the monad. I'm not going to go into more details about that. So, okay, so it's important to say, I think, this thing here is the circuit, this function here. Another thing is the infrastructure necessary to prove a circuit correct. And that's where the formal circuit comes into place. So it's a structure, and this structure defines assumptions, hypotheses, defines specification, defines soundness, and defines completeness. So essentially what we are going to have is the pre and post conditions of a given function. Good node or logic, as we know. And who asked about this? I think that's what you were right. So yeah, what I wanted to say is that on the left-hand side, you have the circum implementation of the E0 circuit. And on the right-hand side, you have the circuit definition in clean. Okay? Which is simply a function, manipulating a monad, as I mentioned before. Okay? So you can see that, you know, it's not very hard to go step by step and see that they're actually doing the same thing, at least for a very simple example. But we need more boilerplate, so to speak, in order to prove this circuit correct. So we need to state which are the assumptions, which is the preconditions for the function, which in this case is true. We have to state the specification, so which is the output or the post condition of the function that represents the circuit. And we need proofs of soundness, and we need proof of completeness. And I'm almost there. Just bear with me a little bit more. So this is the proof of soundness that I wrote. It's actually published on the Clean's website. It's probably certainly can be optimized. I didn't know. What I'm trying to say is that then I knew even lesser than what I do know now. So this proof is probably optimizable, and it can be made simpler. But I wanted to try to use this. I'm going to try something very, very, kids, do not try this at home. So this, can you guys see it? Too small? Now it's good? Cool. So what we have on the left-hand side is the code. So the first, here's the function. As I said, this is the comment with the actual circum description. What you just said, it's actually something that can be, I don't think it's very difficult to take a circum description and generate clean code out of it. They actually have that project, but for a different kind of language. It's like an abstract language for describing circuits. That circum could be translated to that, and that was going to be translated to clean. So they are thinking, or worth thinking about a more abstract pipeline. But the thing is that you can take Circom and generate clean, definitely. And this part here is the function that implements the circuit. And this is a proof of soundness. Okay? So this is boilerplate that we have to write in order to define, in order to prove, I'm sorry about that, to prove a circuit correct. And what I wanted to show you guys is not the details of the proof, but rather the environment. So when we write by, it means that we are entering proof mode or tactic mode. So what we are going to, what follows is actually the application of many tactics in order to prove that the assumption implies the specification, which is the correct, the soundness part. Okay? And as long as we move on each step of the proof, we can see on the right-hand side that the state of the proof is changing. And new variables are being added, and goals are being solved. And on each step, we have to solve them in order to move forward. To that end, we have things like, for instance, the, sorry. If I write the command simp question mark lean is going to try to find solutions to solve the state, the goal in the current state. So if I write simp question mark, it's going to suggest try simp only ID EQ. So this is the simp tactic being applied only using ID EQ tactic. So the thing is that we can, there are commands in tactic mode in lean to help us create the proof. Simp question mark is one of them. Another one of them is RW question mark. That does something similar, but it suggests tactics to be applied in a rewrite mode. So take the tactic and apply it as an equation from left to right. We also have apply, which is another command that tries to find, because we can think of lean as a proof search engine. What these commands are doing is actually trying to find ways of solving the current goals. So these commands help you to identify them. So you see that this apply question mark also produces on the right-hand side some suggestions that you can try. Yeah, that was the, and we use that in order to prove the soundness and completeness of the zero circuit. Okay. There was another thing that I wanted to say. So you see that there are other strategies that, for instance, contradiction is one strategy that I did not mention. And the use of ASOP here, which is very useful to conclude the proof. Okay, finally reaching the end of this, this sharing, if you will. So what I wanted to do here is to share the experience that I had together with Samar. We were working on this together. I did this one. He did many more, very complex ones, inclusive. It was a nice experiment to use Lean and prove a zero knowledge circuit using this approach. I think it's very hard. Most of the time, if the circuit is very simple, you cannot even, it's not even necessary to know the structure of the proof. You can simply try to find it in a prototype way, or a prototypical way, exploring the proof space. But for other certain circuits and more complex definitions, you need to know what you're doing. And sometimes this is not very easy to do, because you have a very complicated circuit and you have no idea how to prove it. So from my thesis that these tools here, because what the clean guys do is to use SIMP as a way to simplify something that they have already written. So I wrote the simplification, which is very complex, or uses a lot of stuff, but I want to make sure that only a certain set of strategies were used. And then if I write SIMP ? Clean is going to give me the strategies that are necessary to solve that goal. And that has an interesting software engineering perspective on that. It's because if Lean changes and what is being defined as the strategies that are going to be applied when SIMP is used, when I use this format here, my proof it's independent of the version of Lean that we are going to use, because these are the strategies that are going to be applied, whether they are part of the annotated with SIMP or not. And I'm telling them, use these rules, and he's going to use them, whether they are part of SIMP annotation, whether they are SIMP annotation on them or not. So my point is that I think sometimes proof search is like prototyping. So we can explore the proof space without knowing exactly which is the structure of the proof that we are going to build. Because sometimes it's just too damn hard. And these are important tools to guide us there. Cool. So Fabricio is going to talk about very neat stuff that Nethermind is doing, using Lean as well. Really excited to hear about that. There are many other DSLs. I'm just mentioned one because that's the experience that I wanted to share with you guys. There's another interesting, or not, path, which is the combination of AI and automatic theorem proving. There's a lot of people investing on that. Recently, there was a proof that was about one of the Erdos problems that was, this proof was found by one of these tools. I'm not sure if it was Alpha Proof or Aristotle. So this is a very important result, I think. And it's a interesting path to follow, to do research and to try and experience what these tools are and perhaps contribute to them. Another thing that I'm looking at is the notion of fully homomorphic encryption, which is very, very interesting. Nowadays, it has it's very expensive, even more expensive than zero-knowledge proofs. But you don't have to create proofs. Okay, you just you have encrypted data and you perform algebraic operations on the encrypted data. And the application of these operations is going to be reflected on the decrypted value. So this is very, very cool, very, very cool. And what about verification of contracts written using FHE? That's something that I think is very, very interesting. So I guess we have a lot to talk about. I'm really, really honored to be here, to have this opportunity to discuss with you guys these things that I'm passionate about. Thank you for giving me for being the second one to talk, because I can now pay attention more relaxed way to my to the following speakers. And thank you very much.
Thank you so much.
Yeah, sure.
So this could be a stupid question because I don't.
No, there's no such thing.
I don't know a lot about ZK, but I know more about me. So at the start of your talk, you were mentioning how it's still knowledge. You have the prover,
Yeah.
whatever. You have a verifier, and
Yeah.
the prover wants to convince the verifier of something without giving the details of the proof, right?
Yeah.
And in this example, or in this idea,
Yeah.
who would be the prover, right? And then who would be the verifier?
No, actually, we are in a different level here.
Okay.
The level it's like we are at design level, so to speak. So I write down my circuit, and I want to make sure that this circuit, before going to production, has certain properties. I want to make sure that this circuit is sound and complete. So I write these proofs. Of course, Lean does have Plonk back running on the back, or I'm not sure how this is used, but what I'm trying to say is that this is for design level circuit specification. So once you are convinced that the circuit has the properties that you want, or once you're convinced that the circuit is sound and complete, then you can put it into production.
So Lean's goal in Clean is to prove soundness and completion, and then send it to.
In Clean, yes, yeah. My personal view is that I think it's way more interesting if we could have tools that can go into your CI. And when you're compiling your stuff, then it can generate a warning saying that there's a proof obligation that you're not fulfilling. So you need to prove this before it goes into production. Okay, so this is, well, I think Certora, for instance, has something like that in their approach, and I think it's the way to go, actually. But to give a short answer to your question, means for design time, so to speak.
So basically,
Yeah, sure.
If I'm designing a CPU circuit, then Clean is a tool for me to make sure that the circuit I made is what I intended it to be.
Yeah, exactly. Exactly that. More questions? Yeah, go ahead.
I can use Lean for write from verification for any type of code.
Yeah.
Okay. You have some cases, or you know about Noir language.
Yeah, sure.
You have some cases for using Lean for.
Do you guys do something with Noir?
No, because the Noir language is a lot more complicated.
Yeah, absolutely.
So
Noir is a, yeah.
So to do something with Noir, you have Rust semantics that I think someone is working. It's called Haus. It's a project that is not only Lean but also Rock to have this Rust semantics. Once you have it, probably be able to use it.
And that's precisely the way I got into this stuff, because as I said, my background is on formal semantics and formal verification. And that's essentially the thing that needs to be done in order to do formal verification in this kind of stuff. So that's precisely the point. So if you want to do formal verification in WAR, if you want to do formal verification in Cairo, if you want to do formal verification in any other way of defining circuits, you need the formal semantics of that, which means a lean, in this case, a lean implementation of the meaning of programs in that language. And then that yields a formal model. This is actually something I had in the slides in the beginning, but I thought it was not necessary to say those. But thank you for your question. So the thing is that we need to construct formally and automatically a formal model of a given program in order to reason about that. Because reasoning is essentially, it's putting the computer to do stuff for you. So you need a formal thing, something that's computable, something that the computer knows how to manage in order to perform a deduction or to prove a theorem. So that's where the semantics comes into place. So when you have the semantics of the language, given a program in that programming language, I can create a formal model and reason on top of it. So this is one form of verification. Another form of verification is model checking that I think you guys are going to talk about, which is a different approach, very useful. It was actually, I think, a very important point in formal verification when Ed Clark and other guys published their book and their work on model checking. But that's it. In order to do verification of a certain language, you need some formal infrastructure to do that.
Like the stuff you talked about, the secure prover, Haus, those are all model checking. I think these all these parts of model checking.
Which ones?
The ones, sorry, the Lucas mentioned, these all.
These two? No.
Lucas?
Oh, Lucas. Okay.
You mentioned the secure prover, Haus.
Oh, yeah.
Those are all.
Yeah, absolutely. Yeah, absolutely.
A cool piece of technique is, I think you mentioned the Rust word. So it's becoming kind of popular. Let's say you want to formalize something about my program in Rust. What do is I compile Rust to something unique that kind of mimics. It has the same semantics. A step in the Rust code is equivalent to a step in this model in Lean. The project that is, I think, it's the most advanced is called Aeneas. I don't know how to pronounce it, but it's pretty good. You can do that for like pretty much any language. But notice that there is a lot of upfront work because effectively, let's say you want to formalize something about my code in Solidity. Now I have a compiler from Solidity to Lean, and now after compiling my contract, I can then prove that, let's say, the contract, it never duplicates money, for example, or like it keeps the balances in check, or that only the admin of the contract can withdraw tokens and things like that. So what it's Cristiano, right?
Cristiano, yes.
Yeah, what Cristiano was thinking about the semantics is that you need to have something in Lean that does the same as your original code. Awesome.
Yeah, thank you.
Those are my questions very much, Professor. The Universal Federal University and learn with you. Thank you so much, Cristiano. Thank you so much. Guys, feel free to connect with me on LinkedIn. It's someone that is very important to people for us and what we're working. And right now, we're going to have my friend Fabrizio from LeaderMind, doing very complicated things as a formal verification engineer. So, yeah, welcome, Fabrizio.
Stop. Obrigado. Parabéns. Se você não está, você tem. Eu tenho.
Can I start? So, I'm Fabrizio. I work as a formal verification engineer at Nethermind in the Lamport team. Today, I will talk about formally verified zero-knowledge virtual machines. And I would like to thank a lot Cristiano, because he made my life so much easier now that he gave a whole lecture about everything, so I can skip a lot of things. It would be a lot easier. So, an introduction about the problems. We at Nethermind, we are mostly focused on trying to take solutions into the Ethereum ecosystem. Ethereum right now, it secures more or less $74 billion in assets. And to prove and do any kind of verification of security in blockchain relies on complex protocols that are really difficult to prove. One big problem of Ethereum is about scalability, trying to increase the size of Ethereum, more transactions. As you can see, one example, right now, Ethereum is only able to do about 18 transactions per second, while Visa can do 24,000 transactions per second. So if you want to apply any kind of Web3 or blockchain to the real world, we have to do a lot more. One possible solution to this that the Ethereum Foundation is betting on is using zero-knowledge virtual machines. It's the same thing as Cristiano said, it's a zero-knowledge proof, but a virtual machine. The idea is that for most of the time, this zero-knowledge protocols was specific for certain problems. But with zero-knowledge virtual machines, any kind of program that you can run in the machine, you already have a proof of the execution. So what is the idea? You run your code locally. Right now, it's not that fast. You can do about 10 seconds of proving using 16 GPUs to prove. So you run your code, you generate a proof of your execution trace, and then you send to the chain to be only verified by validators on chain. As Cristiano said, the idea is validation has to be fast as possible. Some protocols can do it in constant time, so it does not depend on the size of the proof, but the proof can be a lot much longer. At least for the Ethereum, it does not matter as long as the verification is really fast to do it, because you can do it on chain. I will talk here about two kinds of proofs. I think it was one of the last confusions that we have. I think someone asked Cristiano. We have cryptographic protocols proofs. That is the zero-knowledge proof. You have a prover, you have a validator. The prover will try to convince the validator that he knows something, and that is mathematical proofs here. We were talking about Lean. So two different things. We can prove things about proofs of cryptographic protocol, but I will talk about both of them. Here's the bird's eye view of what is the ZKVM architecture. You have your prover, you have your witness generator that will execute your code and generate a trace, an execution trace. The idea here is basically all the instructions that you use to generate this proof or to do this computation. Imagine you have your EMD processor. You have a program that will compile it into x86 processor. Every instruction that it uses to compute some value, you will store in an execution trace. And then you go to the prover will generate a proof. Right now, the fastest ZKVM proof can do this in 10 seconds. We're using 16 GPUs to do this sort of proof as fast. Also, you have a verifier that verify this proof using some kind of cryptographic protocol here. I will talk only about snarks. And to be able to do all of this, you have to have some kind of semantics of your ISA. Most of the zero-knowledge VMs are using RISC-V to do this. But also you can use their own EVM, that it's the Ethereum virtual machine. Or you could use WebAssembly. In the end, it doesn't matter as long as you can represent your ISA in some kind of constraint system. It could be R1CS, it could be Plonk, it could be R, doesn't matter. As the name says, okay, you have a zero-knowledge proof. But in reality, it does not matter for us about the zero knowledge of part of the proof. Zero knowledge, what you gain is basically privacy. But the nice thing about zero knowledge computation and snarks mostly is the succinct part, because it allows you to do any kind of computation and verify it really fast. It doesn't matter if you take 3 years to do a computation of terabytes of data, you can prove it really fast. So you can just off-chain everything and you verify in a constant time in the chain. So to us, that's the really big part, that you can do succinct. And one funny fact, most of the proof system that we have today is not really truly zero knowledge. You can escape, you can obtain information. Because in the end, it does not matter a lot as long as it is succinct. Theoretically, they are, but in the implementation, they are not truly zero knowledge. Our work at Nethermind is mostly focused on this tree, the green part. So we have formalized a bunch of ISA semantics, do some constraint systems. We also work on verifying the protocol itself, the cryptographic part of the mathematical cryptographic part of the protocol, and also the verification of the verifier that lives on chain. And I will talk some examples of each one that we did. And at the end, show one of the tools that we have developed to make it easier to verify this sort of problem. So first, for the verification of the verifier, we did a work with MetterLards with a chain called zkSync that they have a verifier that lives on the Ethereum, so it's written in Solidity. The idea of the MetterLards zkSync is that you have a L2 that does roll-ups. So you do the computation of chain, you submit it to the zkSync, you build a proof, and then you send to the Ethereum via their verifier. And we wanted to verify if the verifier is doing what it's supposed to do. Because imagine, if the verifier is not correct, you can do a lot of bad things. But most importantly, why verify the verifier? Because the prover is really complex. You have a lot of GPU code that for now it's impossible to be verified. You have a lot of low-level optimizations written in assembly, so it's completely unreachable, at least today, to verify the proof. But that does not really matter, because if you have a malicious proof, you mostly have some kind of liveness issues. What it means, you can just disrupt the roll-up operations, or you can generate a valid proof if for invalid computation because of some cryptographic assumptions. So in the end, you can do much harm. You can just, it's somewhat, think about it as some form of DDoS attack. You just, the system will not work, but you can submit invalid proofs. What if you have a malicious or faulty verifier? You have safety issues. One example, if a verifier accepts some kind of invalid proof, that means the transactions can be forged and funds being stolen. And on top of that, you can't trace back the results, because in a cryptographic proof of a transaction, there are no trace of it. So you don't have a bytecode to understand what goes wrong, what went wrong. You can do nothing. So you lost your funds and you don't even know what happens. On top of it, because of that, you can have some serious cryptographic security breaches. So, and even though you have, like I said, you have a malicious prover, but a working verifier, the malicious proof can build incorrect proof, submit to the verifier, but the verifier, as it's correct, will just basically rejects the proof. So there are no problems here. So we work on verifying the zkSync on-chain verifier. We use a proof assistant called EasyCrypt. The nice thing about EasyCrypt that you can prove cryptographic protocols that is different to prove other sort of programs, because cryptographic protocols are probabilistic in nature. You can do that in Lean, at least for now. Spoiler, we are doing this, trying to see if we can do the same thing in Lean. but EasyCrypt can do it. It's probabilistic relational program logics. What does this mean? We can prove properties about probabilistic program, and the relational part, the nice thing is that generally when you do some sort of cryptographic proof, you do it by proving that two programs are indistinguishable. So that's why you need some kind of relational logic, because you want to relate program 1 with program 2 and show that they are indistinguishable by some sort of cryptographic proof. So we have EasyCrypt. We extend it with a subset of U. Why U? Because Solidity changes a lot. We can't model Solidity right now. First, we don't have a semantics of Solidity. We asked Ethereum Foundation about where is the semantic of Solidity, and the only thing they say to us, the actual semantics of the Solidity is the latest version on the GitHub. This does not matter for us. Okay, so, because what, yeah, read the code. But the problem is, okay, we could read the code, but that's not the problem. Doing any form of formalization of any kind of programming language is really hard. And you can do some toy language or a really simple one like lambda calculus. It's really easy to do. But when you have an industrial programming language, it's really difficult, and you don't want anything to change, because if things change, your proofs are not more valid. You have to not redo, but adapt to the new semantics, to the new features that they add to Solidity. So we target U because U is stable more than Solidity. So here we have a extra trusted step. We trust EasyCrypt here to be correctly implemented, and we also trust in the Solidity compiler to be compiling the correct Solidity code. But that's what we can do. So we grabbed only the subset that the verifier uses of U and encoded it in EasyCrypt. We could do this because we already have a U semantics. We had in mind, we wrote this semantics. So if anybody, it's open source. If anybody wants to use this, you can use a complete semantics of U. As I said, EasyCrypt specialized for reason about cryptographic properties. And what we did for now, it's only verifying the honesty. That for us is the most important aspect of a verifier. The verifier implements exactly what it's supposed to do. Okay, we could do soundness, we could do completeness, but from what EasyCrypt allow us to do, for now we can do only prove honesty.
What do you mean by honesty? Sorry.
Honesty it means that the verifier it's not tricking you or of rejecting a valid proof, basically. If the proof is valid, constructed, valid based on the cryptographic protocol, the verifier will accept it. There are no tricks.
So you cannot prove right now that if someone sends you a bad proof, you reject it.
We reject it, basically.
So that's from place.
And also, if you send a valid proof, it will accept it 100% of the time. You guys can read more in our blog post. Most of the work that we do at Nethermind is open source. Most of our work is funded by Ethereum Foundation, so almost everything is open source. Now go to the constraint system verification. As I said, as Cristiano said, we need a formal semantics of anything that we want to prove. If you don't have it, we can do it. There are some options. Okay, we have RISC-V. RISC-V extracted from Sail, from Galois. Galois encoded this incredible piece of technology that you can just extract the semantics of RISC-V into Lean. So that's what we use to verify RISC-V machines. For EVMs, we have the EVM ULean that we wrote at Nethermind. We have EVM semantics of the bytecode, and also for the U. Also, runtime verification has formal semantics of the EVM, so you could use it. From the WAS, you have a formal specification also. Now that we have this formal semantic, we need some way to extract this constraint system into Lean, so we can verify it. There are a lot of projects doing this sort of things, and a lot of constraint systems that we can choose to work on. That is Plonky Tree, I think, is the project that most people are using today. We wrote certi-plonk, that is our extraction mechanism from plonky constraint into link. I will talk more about certi-plonk later. In Rock, Proof Assistant from Olan did also other job doing this. For Halo 2 constraint system, we also wrote Halva, that is an extraction, but for Halo 2. Circom RCS that we know about, that are surveyor from that's written in Lean, and Veridize, you have Picos. For Zirgen, MLR, that's another one that we are almost finishing. Is also, we have this extraction from Zirgen into Lean. You have LLZK, that is a new language that you can express your constraint system directly into Lean. That's being worked on by Veridize. So what properties that we generally want to prove in our ZK VMs? That is safety, that basically nothing goes wrong. When I say safety, it depends a lot on what we are trying to prove. For a constraint system, we are trying to prove that safety against some kind of the semantics, or the proof system that we are working on. We are working on verifying the FRI proof system. It is purely mathematical. We are seeing if the protocol is correct. There are no implementation associated. We have the FRI paper, and we are seeing if the paper is correct. What means we are trying to prove this probabilistic. If there is a malicious prover, if it can generate a proof, there are no witness that the verifier can accept it. The probability is really small. Because again, we are talking about probabilistic program. There is a really small probability that this can happen. We can implement in the verifier. We can verify the implementation of the verifier that we did with ZK Sync. And also we can verify the witness generator. But for this, it's one thing that we are really behind because we don't have a lot of formal semantics to do this. We don't have for Rust. That is Hex that I told you guys that they are working on this for Rust. I think Circon generates, the witness generator is written in JavaScript. It's written in JavaScript, but we don't have a formal semantics of JavaScript. I don't know, but probably not. So we can't verify the witness generator. What about liveness? Liveness is basically saying good things eventually will happen. We can also talk about the completeness. Basically, if the honest prover produce a proof with a witness, the verifier will accept it with a high probability. Also constraint in ISA completeness, we can do this, and prover implementation correctness. As I said, this is probably out of reach for a long time, unless someone wants to verify GPU code. Good luck. Also, you can verify the zero knowledge properties about privacy, but to be honest, we don't care about this. We care that the proof are succinct. That's the way you are interested. For privacy, to be honest, it's just a good thing to have. So, zero knowledge verification. We verify. For this, it was our first experiment doing this sort of verification from Scroll, ZK AVM. We verified their KCheck 256 implementation, their circuit. So to this, we wrote an extraction mechanism called Halva that extract the constraint from their secrets into Lean. As you imagine, why working directly into the constraint and not in the implementation of the circuits? Last year, one example, because we want to have the smallest trust base as possible. We don't want to trust, as an example, Circom. For us, Circom compiler is not to be trusted. We don't know if the input circuit from the Circom produces the exactly same semantically correct output. We don't know because Circom is written in Rust. It can have bugs. So to eliminate this part of the trust base, we work directly on the constraint system. We extract the information. Of course, you have to trust our extraction to work, but our extraction mechanism is a lot smaller than the whole Circom compiler, as one example. So we try to reduce it. Again, we verify the KCheck 256. As you can imagine, how the hell you can verify a hash implementation, because the idea is if you hash something, you just get garbage. how do you verify it? And if you can verify it, you basically broken the hash mechanism. So what we did, we carefully written a keycheck 256 implementation in Lean with the help of the cryptographic team at Nethermind, and trying to follow as close as possible the keycheck paper in Lean. So this is our spec. We could have made mistakes here, but we try to have as many eyes as possible into this implementation to see if it's correct. And for our luck, and not for Scroll, we found a bug. And it's a real important bug, because we discovered that you can manipulate the output of the keycheck for anything that you want, based on certain characteristics of the input. We discovered this. What you could do this, basically in the end, you can have a keycheck value that can be any value as you want. So you can forge things from Scroll. To them, this is not as critical as you imagine, because this keycheck was only used internally by Scroll. So they could say, oh, this is not threatening to us because it uses us internally, but you can think in another perspective, because Scroll could do anything that you want and just say, oh, the proof works. No, it does not work. Scroll could do any other things using this sort of circuit, and told you, no, we did the right thing, but in the end, they could be doing anything. Fortunately, this implementation of the whole Scroll zkVM was sunset, I think, just 2 weeks after we published this. So for now, it's everything okay. As I said, Halva is open source. If you guys have Halo 2 circuits, you can use it. And also, there are a lot more information in the blog post that we have at Nethermind. It goes into the details of how you can fake any value that you want in the keycheck 256.
The bug you found is on zkVM or
is the circuit of the keycheck algorithm for the Scroll zkVM. The implementation, yes. So we also verify SP1 hypercube with certi-plonk. Succinct SP1 uses Plonky 3 as the constraint system. And for this, we verify almost everything of the VM. The specs, we use the 64-bit RISC-V sale spec here that you guys can find. Uses is open source. It's not ours. It's from Galois. We verify 62 opcodes. There are 41 related to ALU operations, add, sub, and their variations. We also verify 10 control flows opcodes, 11 memory related opcodes. And what do you mean? Okay, SP1 has all of these opcodes encoded as a circuit using Plonky 3. We extract this constraint, because again, we don't necessarily trust how all this process, so we extract directly at the source the constraints and verify the constraint. As you can imagine, it's a lot more work, but we reduce the trust base as much as possible. And for SP1, everything seems to be okay. So it's fine, their implementation. We are still not finished. There are some missing opcodes that we have to verify, but it's almost 100% verified. I will talk a little bit about how certi-plonk work right now. I will not go in a lot of details, but just give you a small hint of how it works in practice. As I said, it's basically a framework tool, so you can extract this constraint system from Plonky 3, ZK ADSL, and prove them using the Lean Proof Assistant. We forked Plonky 3 and added a new symbolic builder that the only thing that it does is to extract the constraint. It does nothing more, nothing else. It just extracts the information into Lean to be read, and we can prove a lot of things automatically. And then just the specification part at the end is the user responsibility of their user.
Also, we have a model of the Plonky arithmetics into Lean as a basis for our extraction. And also, we had to write a new tactic in Lean that automatically prove finite field goals. We do this by extracting it into CVC5 and using their finite field solver. But you can ask, oh, but you are trusting CVC5? No, because we modified also CVC5 to extract the reasoning that CVC5 does directly into Lean and replay it back in Lean and see if it's correct. Again, we don't want to add anything in our trust base, only Lean if possible. Again, it's open source. Everyone can open it and experiment. Again, as I said, we use Lean. Programming language, we have an interactive data improver, but the nice thing, one of the most amazing things that the Lean community has ever built is the Mathlib, I think is the largest repository of mechanized mathematics. Anything that you want, in mathematics, there's probably something there in Mathlib. In Nethermind, before starting with Lean, we used Rock proof assistant. But as you imagine, there are no such thing as Mathlib in Rock, so we quickly went to Lean to harness all the power that this have. Why we trust Lean? That's one of the most important parts, as Cristiano told us. The kernel of the Lean is that the only thing that we want to trust. The idea is it has to be really small, and it can be checked by humans. So you can't write another proof assistant to verify there are some computer science things that you can prove about it. There is some complexity about it. But it's our shared standard of truth. For us, Lean is the truth, and the only truth that you want to accept. Because of Mathlib, we can use it as a solid base for verify cryptographic protocols and the foundations. So, to give you an example of how CertiPlonky works, this is Plonky 3. It's Rust. Unfortunately, it's not Lean, but we have to deal with it. Here is how you describe your secret. In Rust, it's not as nice as Circom, but I think you can do a lot more with Plonky 3. So we want to encode a real small problem just to be able to prove it here. Let's prove the property of addition by 8 bits. I want to add two 8-bit numbers, and I want to see if the results are correct modulo some overflow. How we do it? Again, by constraint system. We want our addition, a plus b, to be equal to this result. What this means, r is our overflow bit, so if the value overflows, r will be 1. If it's less than 8 bits, r will be 0, and c will hold the correct result of the computation. This we don't care, but we have to model because we want overflow semantics here. That's how you describe it in Rust. Also, we want to constrain the value of r because we know that r is our overflow bit. We want it to be 0 or 1. Traditionally, that's how you do it. You just say, oh, r to the power of 2 minus r is equal to 0. This is only solvable if r is 0 or 1. Continuing. Our value c will also be represented as a bit value. So it's 8-bit. We can. The idea is to represent c as an addition of C7 different bits. Again, that's how you represent it. Not as nice as Circom. And what we also have to constrain the c's. So for all ci to the power of 2 minus ci, it has to be equal to 0. So that's how someone would encode addition modulo to modulo 8 bits here in Plonky 3. Really simple example, but it's sufficient to show how everything works. How the extraction works, as you can see, there are no Lean here. The idea is we grab the circuit of our clients, we do nothing with it. We just call our symbolic air builder here and just print the Lean constraints. So as I said, this is a modified Plonky tree, But the only thing that we have, we added the symbolic error builder. Everything else stayed the same, so the client don't need to change anything in their part. What this gives us? Unfortunately, there are some manual steps we can automate everything. This will give base constraint simplification, a lot of things. This should be all Lean code, but we have to massage it a little bit to put it in the correct places. But just to give a glimpse what the base constraint is, it's really low level. So this is what the Plonky, our certi-Plonk will generate. The constraints for the first constraint. Okay, first constraint is the 0, 1, but is the one that do the overflow computation. So this is what Plonky 3 sees. This is what we are seeing into Lean. Really low level. We don't want to work at this level. We'll do a little bit of simplification, but this is our base. We have some extra definitions in Lean and also some extra tactics, because one of the nicest thing about Lean is that it's extensible. You can write anything that you want in Lean. You can even modify the Lean syntax to a new different syntax. One example that Cristiano did said that one thing that someone could do it is just add a new parser to circom direct in Lean, that Lean will read the circom directly and just generate what you want inside Lean. You don't even need some kind of extra compiler. You can do this directly in Lean. So at Nethermind, we try to do this a lot. Everything that we can automate or make our lives easier without leaving Lean, we will try to do it. As you can see, we lost all of the information that we had at our beautiful constraint system. There are no more this. We don't know what is A, what is B, because in the end, it does not matter for the constraint system. But for us, proving properties, we matter. It does matter. So we have some extra command to annotate some information that we lost, and we can automatically prove our system automatically prove that these two systems are equal. So here we will be working in a much higher level circuit, if you can say that it's higher level, but it is compared to the other one. But here comes to the human that does the work. This is someone already wrote for us. So this is not generated automatically. Basic, someone has to come and say what the constraint 0 means. For us, it's simple. Okay, you have your sum 2 A and B values, and the result should be something that is multiplied by 256. This is our bit, plus the final result that we want. For the second constraint, again, this starts as empty. Someone has to fill it. Our second constraint, we are constrained to the overflow bit. It's pretty simple, as you guys can see. It's almost, the idea is try to do as one-on-one as possible. And as I said, there are a bunch of properties that the framework already do the proof for us. So this one example that this is our initial constraint, and we are saying they are equivalent to the one that a person wrote. It does this automatically. And also we can deal with interaction or lookup arguments as one example. For this, since the constraint does not do any kind of interaction, we are just saying that the bus is empty. Is one way of saying this. And how you prove things. Now it's the nice part. We want to prove generally soundness, determinism, and completeness for the circuits. This one we are proving the soundness. What it means that if our constraint system holds, this means that our C value will have the correct value modulo 256, that 8 bits. So this is the soundness of the circuit. And again, we prove it. Someone proved it by hand. And again, one of the greatest thing about Lean is their automatic tactics. One example is grind. The other example is SOP. We try to do as much as possible, use them. So most proofs are just basically, you can reduce to basically 4 lines. You do your big reasoning, some kind of induction or case analysis, and then you just grind or ASOP everything away. This is one of a proof example that we can do it. That's how we could verify the SP1. We have a lot of automation, and we use a lot of automation that links already provide to us. So even though this constraint can be really large, really big, we have a lot of automation to do this. So this is soundness, pretty easy to do. We can also prove completeness, pretty straightforward. It means that, if you're, we can prove that exists a valid constraint such that it holds. That's completeness. Here the proof is a little bit longer because there are more reasons to do it. It's not that simple. I elided it. It does not matter for now. So what we are working at Nethermind at this moment, that is the CertiPlonk framework. Again, it's an instrumentation of Plonk 3. In Lean, we have errors, lookup, permutations, everything. A formal model of the Plonk error plus an interaction models. Group-based solvers is the Lean transformation to CVC5 and back to be able to prove, because in the end, as you guys saw, these constraints are basically a bunch of polynomial equations that are nothing more than it. So having a group-based solving makes our lives a lot easier. We also already did a K-check 256 formalization using CertiPlonk. We are also still working to SP1, RISC-V formalization. As I said, there are still some points missing, some opcodes that we want finished. We are working with RISC-0 ZKVM that is using ZirGen. It's a C++ VDSL. Again, what we do, we don't want to work at this level. C++ changes a lot. C++ is a lot more difficult language, even more than Rust. We don't want to deal with this. We went into the MLIR, intermediate representation of Rust. So our framework works by translating, extracting MLR constraint into Lean. We are also trying to work on some probabilistic program logics to try to replace EasyCrypt to be able to prove cryptographic protocols. As I said, Fry, we almost finished Fry. We have we already have some grants to work on Whirl to do this to do the verification. The program logic that we are using is one called Bluebell. It's different than others, but we are trying to integrate it into Lean Iris. Iris is a framework in that you can reason about programs with memory. It's a separation logic. And also, one thing that Cristiano mentioned, we just started working on correct by construction compiler for ZKDSL in Lean. For now, we are targeting R1CS. What I mean by correct by construction, don't mean you are trying to prove if your circuit is correct in relation to a specification. There are two big problems that why we don't trust Circom or any other compiler is that they can generate over and under constraint. By over constraint, what it means, there are some traces that it should be accepting, but you will not accept because your constraint, you have more constraint than the necessary. And the real big problem is the under constraint. It means that you can accept certain problems or certain proofs that is not correct, but since you didn't have enough constraint, you accept it. So the idea is that by this compiler, every circuit that you write will be correct. And in the end, this means that there are no over specification and no under specification. In the future, we want to be able to prove properties about the circuit as Clean does. But for now, what we want to do is only this, and also optimizing, because we don't want to have to write circuits at such low level because it's easy to make mistakes. So the idea is that we'll provide certain gates, high-level gates for anyone to use, and in the end, the compiler will optimize every constraint that it can to reduce the size of the constraint. It's just at the beginning, so I don't have a lot to show, but we are just starting. I think we started 2 weeks ago to do this sort of projects. It will take some time, but let's see how it goes. For the future, we also want to verify others ZKVMs. against the RISC-V semantics. Formalize more proof system. As I said, we are almost finishing with Fry. We already have a grant for Whirl to prove it, but we want to have this Bluebell program logics to be able to do it. We'll make our lives a lot easier to do. And also, we also want also to prove the extraction, prove, verify, or witness generator implementations. That means Rust, or in this case, Mule, that we already have semantics for the ACLib verification. We are hoping that the Hax project will do this for us, and we'll be able to almost close the loop of everything in this AK will be formally verified in the future. So, conclusions. Correctness for the SDK corrections for Ethereum is utmost priority. The formal verification reduces a lot the risks that you can take. Lean for us provided the smallest possible trusted and expressive foundation that we can do it. Because it can be used to unify the verification of ISAs, domain-specific language, constraint, proof system in just one base that you can trust. You don't need to trust anything more. That's it. Thank you for your attention.
Okay, guys, what we're going to do now is, thank you so much, Fabrizio, that was amazing. Thank you so much, brother. What we're going to do now is we're going to do an hour of calls. Okay, so you guys go there, eat a little bit, have a beer. We got to come back in half an hour, okay? So we go with the other presentation. Just relax into your mind, and then we can come back.
Eu não sei se eu vou conseguir citar a dúvida, por isso que eu não falei no meio da apresentação. Mas, tipo assim, como é que você sabe que uma coisa está under constraint? Porque a parada, o exemplo que eu pensei é quando você usa divisão em Circle, por exemplo. Se você usa divisão em Circle, você está fazendo necessariamente uma operação que não é possível de ser constrained. Inicialmente, você tem que fazer o check da vice-versa.
Sim.
Como é que você sabe que isso não aconteceu, sabe?
Então, esse é o problema. Na prática, você não tem como saber, a não ser que você sabe que aquele problema, aquela operação, você precisa exatamente daquilo para fazer, para acontecer. Então, esse é um dos grandes problemas. Ok, eu fiz a divisão, mas será que aquilo é suficiente? Aqueles constraints realmente é o que você realmente precisa? Não tem como saber. Você precisa fazer uma prova para demonstrar que nem mais nem menos. Então, a ideia do compilador é justamente essa. A gente vai ter um conjunto estupidamente restrito de portas, só que cada uma delas você vai ter a prova de que você está exatamente... se o problema está exatamente definido.
Então vai ter programas que não são possíveis de ser definidos no DCL?
Não. Porque a gente já mostrou que se você... uma prova que a gente já tem. Se você tiver gates, vamos pensar em gates, um alto nível, que eles já são provas, eles já têm uma prova de que eles são eles não têm over nem under constraint, a composição deles também respeita. Só que aí, qual que é o problema? O grande problema disso tudo. O tamanho do constraint explode. Gigante. Então a gente precisa otimizar isso. Então as nossas otimizações também têm que ser provadas que mantém. Então esse é um grande problema que a gente brigou com o cliente. Falou, cara, o seu constraint vai ficar maior. Sim, claro, no melhor caso pode ser que a gente consiga. Realisticamente, não. Vai ficar bem maior. Porque qual que é a treta? Uma das operações que mais usa é o range check. Você quer ver se o número está num...
E você precisa de constraint pra caralho.
Você precisa. Range check. Então aí o que alguns sistemas usam? Você faz um cheating.
Lookup.
Não, você pode fazer lookup, mas você ainda vai ter que fazer lookup. O problema é, você fala, lá na ponta eu já verifiquei que esses valores estão no range check correto.
Tá.
Só que aquilo é um programa. A pessoa pode ter esquecido que, nossa, lá na frente eu verifiquei isso, agora não preciso, mas na verdade você precisa.
Você modificou o valor e aí
fudeu. Então é esse tipo de coisa. Então o que a gente faz é todo gate ou circuito que alguém for escrever, ele vai ter tudo que precisa. Então, por exemplo, ok, se esse circuito precisa de range check, a cada etapa ele vai fazer range check. Então você vai ter uma quintuplicação.
De certa forma, é um over-constraining isso.
Você vai fazer o over constraint. Só que assim, não.
Não é um over-constraint per se,
porque você está fazendo.
Você tá fazendo o mesmo check várias vezes.
Mas isso não tem problema. Isso é ok. É redundante, é inútil. Num sistema de equações polinomiais, você consegue fazer a redução polinomial deles e você remove esses casos todos. Você pode fazer. Então, esse tipo de overconstraint é ok, porque o seu sistema que você aceita ainda é o mesmo. Claro, quando a gente fala em overconstraint, é isso. Você tem provas que você deveria aceitar, mas você não vai aceitar. Mas só que se você duplicar um constraint, isso não acontece. Então, isso não é um problema. Só que a ideia é você ter esse compilador, numa linguagem mais bonitinha, em que cada gate é provado, respeitar a propriedade, a composição é provada, as otimizações são comprovadas e a compilação final é comprovada. Aí, pelo menos, esse problema você não tem. Porque hoje, você fala como que você verifica, não tem como.
Totalmente improvável.
A resposta da Legião Foundation sobre isso é tipo, mano.
É piada. Piada, mas vai fazer o quê?
Não, sim.
Opa, boa, beleza. Aquele Felipe, a gente cancelou ele de última hora da outra vez, uma vez. Aí pediu 700.
Tem que falar com
Falar o quê?
Eles não param de mudar e cada vez mais.
Acompanhar o range dele, tem que ter esse meio de fazer. Esse é um problema mais geral. E aí, ele quer mais a gente vai ver isso aí para você, esperar a prova. Essa é a prova. E ela literalmente faz isso.
Very Brazilian, only Brazilian.
E aí?
Aquele cara que ele sempre.
Beleza. Moreninho, né?
É.
Ele tava sem Luma?
Ele tava sem
Ele bem melhor.
Eu vou pesquisando. E aí o sistema de memória dele já funciona muito bem. Então ele fala das coisas já no cloud tira o tempo mesmo botar no sistema de memória, você conectado. Cara, depois dá uma fechada, porque mas o cloud code ele separado, assim, para execução de testes, e aí saiu o Outlook. E eu tô forçando aqui para eu tentar programar uma luz depois.
Eu tô aqui pra minha filha gritando. Vai ser meia hora aqui.
Sim?
Só que em vez de ser, sei lá, 2 na 128, é 2 na 127 de chance de colisão. É um número que não mudou porra nenhuma, tá ligado? Mas a performance do time
Tipo assim, nossa, em vez de você precisar de tipo 2 universos, agora você precisa de
não, é
meio
pior.
universo.
É você precisava de 2 na 60 universo, agora você precisa de 2 na 59. Não dá.
Não vai quebrar.
Exato, exato. Em compensação, se você for ver com a criptografia assimétrica, elíptica, RSA, etc., é muito mais fácil. É uma ordem ainda assim, você precisa de alguns universos, mas ele, tipo, muda de mano. Você precisa de trilhões de universos, é tipo, 2, 3, 7, ele é muito problema, mas sei lá, só ver o hate de cripto no geral. Mas agora eu
Inclusive, eu perguntar se nessa parada de AI que você vai trabalhar, se você vai estar aplicando qualquer coisa de verificação, tipo, mesmo que seja muito assim, diretamente.
No momento não. A gente está pensando em paradas. Basicamente, eu penso que, por exemplo, o simulador de Rust para mim, eu queria muito fazer um JavaScript na semana de JavaScript. E esse mês que JavaScript
Deve ser mais. A semântica de JavaScript.
Não, a semântica de JavaScript.
Em comparação com você mais. Ah, tudo bem, tudo bem.
Não é comparado com você. Só de não ter um desenho na linguagem já é uma parada muito massa. Mas aí a gente está pensando em paradas assim. Aqui da projeto, a gente levantar mais dinheiro aí. Eu vou dar um pouco. Vamos lá.
Eu não sou bom com nome. Ah, não, mas é seu nome. Quem esquece? Você não gosta disso? A gente não quer. Nada. Eu conheço um cara que se chama Gui. O amor dele. O nome dele. Eu pago de meu pai, mas. Cara, eu não interesse mas depois foi voltado outra coisa e hoje o nosso founder na verdade, eu tenho uma ideia bem louca que eu queria só para de type system, uma linguagem homomórfica e self-purpose, independente mais. Independente, cara, que se resolver todos os nossos problemas, uma bala de prata. Cara, eu fiquei muito tempo, mas eu não entendo nem de type system direito, nem de schema direito. Eu tô.
Guys, party's over. I'm going home. Take a seat. We're about to start again. I promise no cops showed up. We don't want you to. That's not the party.
Awesome. Thank you so much, guys. Now, Gabi and Eric will give us an amazing talk about Quint.
So, anyone try the chicken heart?
Really good.
Chicken heart? I saw some faces with chicken heart. So Brazilian barbecue is very traditional like this. You don't get a plate with your own kind of like steak. You're supposed to just play and get with your own hands a little bit of food, and this keeps going for hours. So the idea today was to give you guys some cultural immersion of what it is to be in a Brazilian household for the weekend. This is usually how our Sundays go at our own house. And then Brazilians eat chicken heart, which is very unique. But then also they love picanha. So there's still some meat. If you want, you can get a little plate, or we're still gonna keep bringing some. Ready? Let's do it. Hi everyone. This is a talk about food. And also we'll be talking about LLM. So sorry. Short intro, we are also in Brazil. We work for informal systems. We are like the only people living in Brazil on informal. And this is to and for Brazil's mission is to foster trust in software and money. Today I will hear in software, but I can also like try to talk about the parts later. But here we're going to talk about software. And the way we do this is mainly through a tool called Haus, which we started doing 4 years ago when I joined.
Sorry. Good, sorry. So Quint, and this tool has helped us to increase confidence and like reliability on the software we developed. And we are going to show you a bit how we can also use that to superpower the AI workflow and solve some of the problems with it. But first, like I just put the slides just to add some context through all the other stuff that we talked about here today. So there's fuzzing, there's model checking, and there's proofs and proof assistance, right? And with Quint, you can do both fuzzing with the Quint simulator, and you can also do model checking if you do transpilation to TLA+. I'll talk a bit about TLA+ later, but just so you know, you can do fuzzing and model checking. We cannot do proofs. I would like to. I actually talked to Elias Sergey about the possibility of embedding Quint into Lean. So perhaps one day, if anyone wants to try that, talk to me. But we use model checking. And model checking will work either by enumerating all possible states you can reach and then verifying a property on all of those states, or verifying a property in all of those states. Or we can also do model checking by solving constraints. So translating your thing to constraints, then solving them, and looking for property violations with SMT solvers. Okay, so
solving the constraints is building a proof, like because it says you can do a proof.
no, because you cannot inspect the proof. So basically, what you're finding, if the SMT solver replies satisfied, this means you don't have a bug. If the SMT solver returns unsatisfied, then you can see the values, the assignments for each of the value in your constraint that will lead to the problem. Yes. So
look at how it's saying like if it's consistent.
yes. Yes. And then you have to understand how Z3 or other SMT solvers work. And I don't really know how those work. I just know what they do. Sorry? Nobody knows, except like 2 people. And one of them is Brazilian. Yeah, so we have model checking and we have fuzzing. And then why, right? If you can write proofs, then why use Quint? We usually use Quint when in systems where it would be just unfeasible to do proofs. So we've seen here how much work you have to put into getting a proof, and not every time this is worth it. So the types of things you use Quint for at Informal, for instance, is consensus protocols and decentralized exchanges. Okay? So Gabriela, should I use a proof or should I use model checking? You have to think about your relation of cost and risk, right? So for instance, we saw that zkAVM they will be securing so much money in Ethereum, right? That it's worth for their Ethereum Foundation just to pay Nethermind a bunch of money, and also other companies a bunch of money, right? There's a bunch of money involved. It's super hard to do this, but it's worth it because zkAVM will just secure so much money that it makes sense to put all this money. Okay? But most of the time, this is not true. Most of the time, people don't even want to do formal verification. Okay? So model checking is something much, much easier than proofs. Then fuzzing is something much, much simpler than model checking. So we are just kind of like trying to bring this better tools for more people. So just so you have that framing, proofs are great, you love them, but sometimes it's not possible. That's when we have Quint. So now for the actual talk, that this was just I added for the content. We are going to talk about a bit of a challenge in the AI world and the solution that we came up with, the experiment we tried, which involves a specific workflow we came up with, and the insights. Okay, so it's a very like use case practical talk. So for context and the problem is the state of trust in software. I think we talked here about like how much software is securing a bunch of money. And when you involve AI, you might have noticed that AI trusts a lot in the code it writes. It's like, I know it. It's very happy about the code it writes. And the problem is it's really convincing. The whole point of LLMs is not to produce correct things. It's to produce things that look correct. Okay? If this is a hot take, we can debate later, but I think this is true. And then the problem is that reading AI-generated code and determining if it's correct or not, it's super hard. Like it's literally a tool optimized to be convincing. And now we are tasked with determining if it's correct or not. It's a big challenge. So we are going to play a little game of bingo. It's not interactive. You can just raise your hands. I don't have an app, sorry. So who here has stressed over a huge AI diff and had no clue if it was right or not, just stared at the huge AI diff and wanted to cry? Okay. Who here has been fooled by AI with code that seemed to work, but actually was doing a trick, like a hard-coded thing? Like you might remember at some point. Who here missed working with code and structure after like endless times of working with agents and prompts and lack of structure and just natural language? Me too. And who here has had AI written tests for them? And the tests were all passing, but they actually were not testing what you wanted. Okay, all of us fooled by AI. And then the point I wanted to make is that the challenge with AI is not generation anymore. AIs are great at generating things, but it's to validate what they actually generate. I want to talk a lot about validation here. And sometimes humans are the best validation, especially with visual tools that we can visualize. For instance, I wrote the slides with Typist, it's a tool, and then so that all the templates and some stuff were vibe coded, and then I asked Claude to generate for me a decentralization visualization for me to put on my slide, and I could immediately tell this was not good. Okay, so when we have ability to visualize things, that makes AI nice to use. But what do we look at if you want to validate a decentralized system? We usually don't have something to look at. We usually have a hard time testing, like we don't even have a CLI thing that we can run and see if it works or not. Like we usually have to do a bunch of orchestration. And even if we have a bunch of logs, reasoning about those logs is super complex because those are distributed logs. So it's super hard to do anything about a decentralized system that makes us tell if it's correct or not. So for decentralized systems, it's very challenging to validate. Let's continue the bingo. Who here has generated something with AI and immediately saw it working? It's amazing. Sometimes it just works out of the box and it's amazing. And who here was mesmerized by having AI running the compiler and fixing its own mistakes? For instance, like switching to Cloud Code or switching from ChatGPT to Codex, and then it has the compiler. It's so amazing. The first time I saw that, I was like, yes. Who here has used AI to format or organize something and it instantly looked better? Right? So when we have something to visualize, like or something to validate quickly, like with the compiler, then it's amazing to use AIs. Or when we have like something simple enough that we generate, like a simple website that we can look at and it's there and it works and we are happy. Validation is very good. So defining correctness, defining what is right and what is not, is what superpowers AI. And so let's talk about defining correctness. And then there is this thing now, you might have heard, called spec-driven development, right? And then a few months ago, I saw this talk on YouTube from Shem Grove from OpenAI. The talk was about the new code, that was the title. And the guy was talking about how written specifications aligns humans and how that is the artifact that you communicate, discuss, debate, and think on. And I was like, yes, specifications aligning humans. And then I realized he was talking about natural language. English. Yay! No, that doesn't have problems, absolutely, right? So yeah, if you don't know the problems with doing that with English is that it's very easy to be ambiguous. Even if you're super smart, even if you're Leslie Lamport, if you're really hard, trying really hard not to be ambiguous, we're still going to be ambiguous. You cannot reliably connect it with code. The best you can do is like, hey AI, is my documentation corresponding to my code? And the AI says yes, and we're like happy. But you cannot actually have some checks there. And most of all, it's hard to validate because the only way you can validate is just reading it, and that's annoying. So I don't like natural language. So executable specs are the solution we are proposing to this, and that's the ideal validation. So what are executable specs? Quint. The Quint is one executable spec, and just for some context on how we came up with this like executable spec concept. So we created Quint as a developer-friendly syntax for TLA+. Who here knows TLA+? So it's a point. A lot of people. I will show you a bit of TLA+. TLA+ is a formal specification language, formula checking, that is very popular. It's used by Amazon, Intel, Microsoft, etc. But it's a nightmare. So we made Quint for a more developer-friendly, a better syntax, okay? And one thing we noticed is that with TLA+, when people were learning TLA+, they would always ask, how do I run it? Okay, we wrote code, now I want to run it. And then, no, you don't run it. No, you model check it. Okay, but how do I run? No, you don't run it, you model check. And people were pissed. So we decided to create a Quint run command that would address this. So now you can run it. And this would just like do one random simulation of the model will show the result. And people were happy. So yes. But then this became actually much more valuable than just this like small thing. Because we realized that we were finding a lot of bugs just with random simulation. We didn't have to like do our whole orchestration to do model checking. Just random simulation was so good already. And we are using, that's the main way in which we are using Quint today. So many problems, it's not feasible. We don't have time to do model checking. Just the simulation just gives us enough confidence. And it's great. So maybe I'm here talking in a formal verification company about not doing formal verification. But let's take it slowly, you know, like we are trying to bring this to the industry. And And this is already like helping with reliability, which is the main point. So just for the ones who haven't seen a TLA Plus, here's how a TLA Plus spec looks like. This is the same code in Quint and TLA Plus. Sorry, it's a bit small. But in TLA Plus, basically, you have some math symbols. You have a very weird syntax for updating anything. So you have this except, and then you have a bang, exclamation mark. And in Quint, everything is like, it's more like longer, okay? You have to type more, but it's easier to read. It's easier to remember how you do something. You don't have to like look it up every time because everything's like very memorable. That's the main point. We have some extra stuff as well, but it was born as a syntax, just to make that point, but it's not important. And then we have some concept of executable executions, right? Because when you have an execution of a distributed system or any system, how we usually express that is through some drawings or some diagrams. Right? So you go on a whiteboard, say like, oh, this node sends this message, and then this node sends this message, and this is a concrete execution of a concrete consensus protocol that we were studying. Okay, sorry about that. Let me mute it. Look, thanks, Kevin. Kevin just sent a photo. This was supposed to be showing up here, so I'll fix that in a bit. So yeah, so this is how an execution looks like, and in real life. And in Quint, you actually have something like this. So I personally believe that this is better to understand than this, but this can be argued, okay? Because here you can actually read what's happening. You can actually, I think it's easier just to see the arrows, but that's very personal. But the point I want to make is that this is executable. You can ask Quint, like, is this a valid execution of my model? And then it says, right? So if you forgot to draw an arrow, here you never know, right? Unless you're really smart and spend a lot of time staring at this. But here you definitely know. And this is a great way also like the people that are working on the algorithm on the protocol to communicate with the engineers. Because they say like, hey, engineer, this is the thing that has to happen. And then the engineer knows exactly step by step what has to happen. It can write a test from this, etc. So those are great as well. So that's the concept of like executable specifications, executable executions. It's still something abstract, but then you can actually simulate, you can run. And you can model check, but we don't talk about that a lot. We just say to people executable specifications, they are happier that way. Okay, so now to the point of validation, AI, and where Quint fits into the story, and why Quint can be a solution for the spec-driven development story. Because Quint, or executable specs, they sit between English and code. So on one side, you have English, which is abstract, and therefore hard to validate. You can only validate it by reading or by asking LLM to read it for you. It's ambiguous, as I told you, and you have no mechanical validation. Let me stop my Telegram, please. Because no one ever messages me, and then I open my Telegram, and now, of course. And also, like, I don't know what's happening because it's supposed to show the notifications on this screen, so I don't know what happened. Is it working? Sorry. English. So you also don't have any mechanical validation. You cannot say like, oh, is this is all my definitions previously defined, or all my interfaces matching? You know, like type checking. You don't have any of that in English. In the other side, you have code. So you know, like in AI, you usually go straight from English to code. Right? So on the other side, you have code, which is highly detailed, and that's what makes it hard to validate. Because it's a lot of details. You have like a bunch of logs. You have a bunch of, are you using protobuf or JSON to communicate? Are you using whatever? There's so much detail that the core functionality that you want to think about is like messed around, hidden in all the details. So it's hard to validate. You can still validate structural parts like parsing, type checking, which is great, but it's still very hard to validate correctness, as I guess you got from the other talks. So in between, the sweet spot, we have Quint, which is abstract. So you can stay on a level similar to like pseudocode. You don't have to like go into all of detail in code, but it's precise. And you can do mechanical design level validation. So you can validate properties, validate lots of different things, not only type checking and parsing. And you can have a mechanical connection with, by mechanical here, I mean that's not AI, like it's actually deterministic. So you have a mechanical connection with code. Make sure that your code is matching your spec, at least in some scenarios.
So we wanted to try out all these ideas. the idea that we could use Quint and leverage this new wave of LLMs to sort of help us build systems, more correct, so to speak, and faster. And we decided to run a real experiment. We're gonna talk about a complex system. We wanted a complex system because the theory is if it works for a sufficiently complex system, it should also work for something a bit smaller, a bit simpler. We just didn't want to take like a toy project and where we can control very much all the variables in the output. We wanted something more substantial. We decided to use Malachite. Malachite is a BFT consensus engine that was developed by Informal. It is an implementation of a tournament protocol, has lots of nice optimizations, and it's generally an easier library to use. It has been acquired by Circle, the creator of USDC, to build Arc. And it has the advantage that Malachite protocol was designed and done with Quint. So there was a lot of Quint expertise already in-house of how that system works. And the change that we wanted to make to Malachite is change it from traditional Tendermint to a fast Tendermint protocol, which it trades performance for fault tolerance. It might just look like a different quorum, but it's actually a different algorithm altogether. And the traditional estimate for this body of work is that it would take maybe a couple months, right? And we challenged ourselves to leverage Quint and AI to maybe do it in a week. And we did. So our starting point was a Quint specification. We already had a Quint specification for the old version of Tendermint, like the version of Tendermint that was implemented. We didn't just we didn't just tell AI like, can you get the specification from the code? Like that's one thing that we actually are going to look at. Like the idea of mining and a specification from the code is just another way of getting started. But we already had that specification. But I would argue that even if you don't have an specification and you need to write that by hand right now, it's still valuable, especially after we present all the tools and all the workflow that we have built, because it then helps you with subsequent changes to the code base and validating your ideas, like how am I going to change the system? Can I change the system and keep the invariants and the properties? It's still helpful, especially in systems of large scale where complexity usually compounds fast, right? So we wanted to make fast Tendermint. We didn't just give AI like, hey, can you please make it faster? We believe humans are the best designers. And we actually have a really good designer called Manu. He's one of the best protocol designers that we know of. He works for us. And he sat down and he looked at the protocol. He looked at everything and designed fast Tendermint, a variation of Tendermint algorithm in English and pseudocode. And he did all the the mathematical validations by hand. So we ended up with a really good description of what the algorithm should be and some pseudocode to help us. So with this inputs, the original Quint specification and the English protocol, we design a workflow. This workflow is composed of 4 steps. The first one is we wanted to take the previous Quint specification and based on the English description, change that specification to match the new algorithm. Then we want to do spec validation, make sure that the new spec is correct, it has all the properties that we want, all the variants that we want. And from there, we wanted to do code changes, look at the old system, look at the new specification, and make the necessary changes so the system now behaves in the way we want. And we also wanted to do code validation. We want to validate that the new code is correct according to the new version of the specification. And we wanted to do all of those steps with Quint and AI. So the first step is changing the spec. So we started with the old Tendermint specification in Quint and Manu's English description of fast Tendermint. And the process is AI is going to modify the old spec to the new protocol description. And at this phase, it's only going to run the most basic commands like Quint parse and Quint type check, just to make sure that the generated new spec, it is sort of correct. Like it doesn't have syntax errors, the types are aligning, everything like just kind of looks okay. It's just some basic reality checks and guardrails around the behavior of the AI. It's not going to hallucinate syntax, for example. There is Quint type check and Quint parse to make sure like it doesn't go sideways. Then it comes the real interesting part, which is spec validation. Like, does this new spec, is it correct? Like, does it have the right properties? And that's where you can ask AI to sort of like, hey, suggest me a few scenarios, a few witnesses, a few invariants. But this is kind of a challenge for AI. Like, again, humans are the best designers. That's where you bring your expertise as a designer, and you interact with AI to explore and validate your specification. The AI, at this point, it knows all the tools at its disposal. It knows the syntax of the language. So you can ask AI, like, can you find me a scenario where something that I want happens? And it will, by itself, write a witness. It will run the Quint tool and try to find a witness for you, right? And this process, you gaining confidence that the new specification, it was generated by AI, but you interacting with this AI system, you gain confidence that the new specification is correct.
I just want to add, because we talked about witness before, and we are not talking about the same witness here. So just to comment, what we refer to as witness is a non-property. So a property that we expect to break, and then we check it if it actually breaks. And this is a way to play with liveness without actually verifying liveness, which can be complicated. So we say, like, can I reach a scenario where a certain thing happens? And then we run the simulator. Simulator finds that scenario, and that's what we call a witness. Oh, okay, so my protocol can reach a state like that. Okay. Sorry, go back to Eric.
So this is an example. We ask the AI, like, this is a command that we ask AI, just, go ahead, generate some witnesses for us. It will propose a few, just common witnesses that it knows of, like checking for liveness, witness, or other properties that it kind of understands from the specification. And you, behind the keyboard, you're going to select the ones that you want, or maybe you're going to suggest AI to find other witnesses that are of interest, right? Moving ahead, it will say, hey, okay, based on your description, I'm going to generate this witnesses for you. I'm going to check if they all actually occur in the specification. And what we found is that AI is good at finding bugs. When it finds a bug, it can usually pinpoint exactly like, oh, there's a bug here. There's an example where one of the variables in the model was not being modified correctly, found the bug. And when he finds the bugs, especially when he finds like witnesses of something, it is actually really good at summarizing what it found based on the specification that you gave it. The next slide, there is an example. Like, hey, here's a witness. It has 28 steps. So a human being looking at 28 steps, tracking all these variables, is incredibly difficult to understand exactly what's happening. But AI, looking at the model and looking at the output, is really good at summarizing things and says, well, there's a phase 1 that is a proposal. It happens between steps 1 and 10. There's phase 2, a pre-vote collection, steps 11 to 28. Everything was kind of right here. And then on step 28, there's a key event. Something happened. And then at step 29, there is the witness that we found, right? AI was a really interesting tool to sort of summarize all of that output and give us something that is a bit easier for humans to digest and pinpoint what's happening. Okay, so spec validation brand, we actually found a few bugs in a few hours. And the bugs came from the English spec, which was great. Like, this is the best moment to find a bug, that there's no code written, nothing of substantial cost. So it's a great moment to find all the bugs, really refine that specification. And once you gain enough trust that this is the spec that you want to move forward, then we can go to code generation. In code generation, the approach that we took is we give AI the old Quint specification and the new one, and we ask the AI, find the differences between the old and the new spec, and then look at the code and find where those differences should be applied. And it turns out the diff is an amazing input for AI, because it really pinpoints exactly what has to change. So if you have an old spec and a new one, it will give you exactly what has to change. And AI, it will still have some trouble if most likely the level of abstraction between the specification and the code are different. It will still have a hard time sometimes finding like, oh, this is too abstract in the spec. I need to be very precise and very concrete in the code. And AI usually hallucinates around things that it doesn't understand. We wanted to take a different step So we specifically instructed our agents to not go sideways and actually ask the human behind the keyboard. So this is an example. There is a new field in the new specification called max rounds, and the AI found 2 possible places to put that in code. And instead of just picking one or maybe picking a random place to put that state, we instructed the AI, come back to us, and we're going to guide you. And this is exactly what's happening. It's saying, well, I could put it in the state machine data structure, or I could put it in the vault keeper. 2 different data structures. I could put it in any of them, or you could even tell AI, like, oh, I'm going to decide later, or I'm going to give you now the instructions of where to put this field. So again, just brings back the human behind the keyboard as the best designer that there is to make the choices, because you know the code base, you know where things should be, not the AI. But the AI is really good at finding those entry points and asking you what you want to do. So then comes code validation, right? We have the spec, we played with spec, we have a new specification. We are now generating code. How do we know that this code is right? So this is a process. We put a step 4, but it's not actually step 4. It kind of intermingles with code generation. So every time there is enough code generated that we can introduce a model-based test that will verify that code. That's what the AI is going to do. That's the workflow is going to suggest you to do that. And here, the AI, traditionally, like if you're unfamiliar with model-based testing, like what you do is like you run your formal method tool. It was going to generate traces, and traces are a sequence of steps that are valid according to the specification. And then you're going to replay that against your code, and the state of the spec and the state of the code should match, right? There's usually quite a bit of boilerplate code that you need to write to connect those 2 together, right? You got to look at what the traces are telling you to do. You got to find the code that does that. You run it, and somehow you got to extract the code, extract the state from the application, and move it back so that we can verify it against the spec. There's code involved, right? We have designed a library to minimize the amount of boilerplate that you need to write, but there's still some boilerplate. And we found the AI is exceptionally good at finding those entry points and generating that glue code, that boilerplate that connects the 2 of them. So here the AI will generate a code that will use this library to model-based test your application. And this is code that lives in your CI. Every time you make a change, if it doesn't conform to the specification, the test should break, right? And here is a moment that this is very close to my heart. This is a moment where we take that spec that a lot of times people will just throw at a corner when they start coding and never look back. And we bring it back as a live artifact that lives in your development environment all the time. Like you can't just change stuff that doesn't conform to the spec anymore. The library and this process will guarantee that it is conforming as you make changes. So this is incredibly valuable. So for the steps, we are thinking and designing a tool for trace validation, which is just a little bit different, is the act of instrumenting your code so that every time there's a trace that comes from production, or maybe a test environment, or maybe some other test that isn't a model-based test, if you can compose a trace that you have actually observed in production or some other environment, you take that trace, move it back to Quint tools, and have that trace being checked against your model. So this is a one step further that we're working on, but not quite there yet. So here's an example of a test. So this is generated by AI. This is part of our library. We call it Quint test. And you point to the specification, the model, and remember those executable runs? They have like run and then the name of the run. You can put them here, and now you execute them on your code every time. There's also a simulation mode if you just want to run general, like random simulations, random traces from Quint. There's also a Quint run that will let you do that. So you can run those, like the things that you have specified as a designer, like I know these things should happen in this sequence of steps, and these are correct or not. But you can also just let the tool generate random traces for you. This is an example of a glue code. This code has not been written by a human. The AI has generated this, and it is based on the specification and based on the AI looking at your implementation and say, oh, this is the entry point that I should call every time there is a Quint call to decide on proposal, right? So how we did all of this? Like at the beginning, we were like, let's give Claude the tools that we have, like the Quint specification, the English description, and let's just sort of guide the AI to the right path. And that took us about a week to complete the experiment of producing fast intermittent monoclite. And then we decided, let's automate everything that we have. And we ended up with 2 MCP servers, 5 agents, 14 commands. And this is just in a library that I told you. And this is just the embodiment of all of our expertise in designing and building the systems in a way that can be reused by people who maybe, they're not very familiar with Quint yet, or maybe not very familiar with how they should do model-based testing or how they translate Quint into code. This is how they can tap into that knowledge through tools that can be generally reusable with AI systems. After that automation, we ended up rerunning the experiment and took us about 2 days. So a really good performance improvement there.
Okay, so close to wrapping it up, some key insights from this experiment. First one, this is something that we didn't expect, and it was very nice to see, is that the validated spec, having a validated spec in this workflow prevents us, and prevents especially the AI from diving into non-issues. So something we saw a few times is that, so AI was struggling with something, like the test was not testing, and it was trying to debug. So AI goes, writes a bunch of logs, and it was reading its own logs and trying to figure out what was going on. And suddenly it was saying, oh, I know it's wrong. We should be broadcasting X when we do Y. He had an hypothesis. And at that point, I was watching it work, and I almost stopped it. I was like, no. Because if it started doing that, it would try to implement a new broadcast, and then everything else would break. And I was like, no, that's not how we should solve it. But I decided to wait a bit. Let's see what happens. So I didn't intervene. And then what happened was very interesting, because AI was referred back to the Quint specification. And it saw, oh, actually, that's by design. We actually don't broadcast X when doing Y. So that's not a problem. And it moved on to other hypotheses and eventually found the problem. So that was amazing. But then you can say, Gabriela, but okay, if you had a documentation in English, if you had Mono's specification in the AI, that would also happen, right? It would consult the English document and say, oh, no, that's not here, so I should not do it. And I claim, really? Because wouldn't you second guess the document? Wouldn't we maybe think oh, perhaps Mono forgot to write this, or perhaps Mono made a mistake, perhaps this is not working actually, perhaps we need that broadcast. But in this case, this doesn't happen because we know that the Quint spec works. We already validated it a lot. We already ran witnesses and properties. So we know that the spec is correct, and it's able to accomplish what we want without broadcasting it while doing what. So we don't second guess the artifact because the artifact is already validated, and that's why it is a better input for AI than just English. And this makes us confidently rule out false hypotheses like this. Another insight is something that actually blows my mind, because Quint, I told you, we started it 4 years ago. We didn't talk about LLMs 4 years ago. Quint was never a tool for AI. I started introducing AI in my vocabulary months ago. Okay? Quint is something built for humans. We wanted to make the same things that the other guys here were talking about. We want to bring formal verification to the industry. We want to make formal methods more accessible. It was a tool built for humans to reason about complex systems easier. And we realized just giving Quint to AI just help it guardrail the AI enough so it can work with more complexity. So far we can use LLMs up until a point, right? And if we give give Quint to the AI, and then it can work with even more complex systems because it makes things better to validate. So learning here, instead of putting AI in everything we build, perhaps we should give the good tools, modesty aside, to AI. And since our work as developers is shifting a bit from writing code to validating code that AI wrote, perhaps you didn't start that yet, but future is coming. I think that's a tendency. So we are less and less writing code and more validating what AI wrote. In this case, we need the best validation tools we can find, and defining what correctness means is super important. And lastly, LLMs here, the LLMs are translators. They are not designers, and we are using in this workflow, we are using LLMs where they excel at, which is language translation. They're great at that. We translate between Quint specifications, written documentation in English, to papers, to implementation codes. All of this communicate, and Quint specs are in the center. And we are not asking AI to either design or also to reason about correctness. All of the reasoning, all of the like checking if this can happen or not is done through the Quint deterministic tools that do not involve AI at all. So LLMs, they don't think, they just translate between things. So you maybe thought I forgot about the bingo, but let's finish it. Who here has used AI to convert things from one programming language to another? It was very cool at the beginning. Who here has used AI to help you understand some logs? These are just some examples of how AI can be used as a translation tool, and it's great. Okay, so just to validate my last point. But what we see with the bingo, the idea was that when you have no validation, like huge diffs, endless prompts, testing, AI fooling you, when you have no way of validating, it's painful to use AI. It will fool you and you feel frustrated. And when you start having validation, like when you have something easy to look at, a document or the compiler, then AI becomes amazing because they are great translation tools as well. This is the last slide. We are doubling down on this. Look, we really like the workflow. We are super happy with the results we achieved. So like Informal is really doubling down on this when we are trying to like scale up our efforts. We are trying to find also like projects that are complex enough that can take advantage of this. So if you have one of those, let's chat. We can follow me on Twitter. Eric doesn't have a Twitter, but he has LinkedIn. So you can find us on LinkedIn as well. Also can connect on Telegram. We have this website, quint-lang.org, where we have a blog post about all of this that I explained. So everything's there explained. And you can join our Telegram group, which you can find in the website as well. Yeah, I also have a bigger demo for this. So we showed a few screenshots. I have a fuller version. So if you want to see more detail about that workflow, I can show you. If you have an interesting project you want to try this on, get in touch. Let's figure out a way to collaborate. And let's shift from reading a bunch of code to playing with it. And
wow.
This is it.
Guys, please, everybody, take your phones off your phones right now. Let's follow Bugarella here right now, everybody. Yeah, go on, please.
Did you have to train your AI models to understand the right thing?
No, we only wrote agents. So it's all, we use Claude.
So like Claude already knows Quint well enough.
No, that's how, it knows a little bit of Quint. It's getting better, every model. But that's the main usage of the MCP server. So the 2 MCP servers we wrote were related to getting Claude to understand Quint better. One of the MCP servers is a knowledge-based server, where if AI is trying to write a Quint spec, it can consult Quint's documentation in a better way. And the other one is a connection to Quint's LSP, language server protocol. So it kind of like can diagnose its own errors. It's kind of like it's using an editor then. So the 2 MCP servers are the things that help AI use Quint, but those are not like retraining the model. Those are things you plug on top of Claude or the other AIs.
Just one thing that I think complements this is the fact that Quint was written for developers, so the syntax is already much familiar to other programming languages, similar to other programming languages, so the AI has an easier time doing that translation. It looks like, you know, JavaScript, maybe.
Awesome. Thank you so much, guys. Eric, Gabriela, please go on.
Yeah.
Sorry. Yeah.
I would like to know if temporal logic is also used in the process to do all this amazing stuff that you're doing. So it's not, is it only the definition of the model that you're taking into account, but also properties specified in some temporal logic?
We don't use temporal logic. We can. So Quint supports the same temporal formulas as TLA+.
Yes.
We find that's very advanced. So only like very advanced. So only like very advanced use, like probably if you guys would use Quint, you would use temporal formulas. But for most users, that's not the case, because you only actually need temporal formulas for liveness. And verifying liveness, not safety, because safety is something that you don't want something bad to happen. Right? You want to reply, or do you want another question?
No.
Okay. So wait for you. Safety properties you can express like, this never happens, right? Something bad never happens. And that's an invariant. That's true for every single state of your system. So you don't need temporal logic for safety.
I think it goes, like, your question goes into the, you know, how confident you are in the specification that you wrote. And I think this is like the final step. If you have a specification and you have done all the simulations, you have proved some invariance maybe, and you want to take that step further and say, okay, I'm absolutely sure that liveness is preserved. Like you go into that direction, you gain more confidence. But that's, I think, orthogonal to the work that we presented, because in a lot of systems today that we use every day that have no formal verification whatsoever, like just gaining confidence in some invariant, or maybe gaining confidence that the system sort of behaves through witnessing traces that are valid, is enough confidence that it can still be useful in the context that we presented. But I agree, like if you want to take that step further into, that's where you go. Yeah.
Just sorry, one last question. Recently, I came to know about an approach called memory bank that people are using to, make AI more. You don't have to waste time telling AI to correct itself, for instance. So I was wondering whether you guys use that somehow, or you find it interesting. It's just out of curiosity.
Yeah, I haven't heard of memory bank, to be honest. The third member of our team, like of the core team that work on this, is not here. He's the one that understands about all AI technology better. But the agents we built, they solve this problem. So just go quickly back to the workflow here. Use this slide that you see on top. The spec change, that's very independent. You just like say, generate spec from this like English description, and you can go away from the computer. When you come back, it's done. So we don't have this problem because the agents, they know how to run the Quint tools. Fine. Oh, this is a syntax issue. It goes and fix it. Oh, it's a type checking issue. It goes and fix it. So this first part is completely independent. The second part is iterative anyway. It's when you play with the spec. So there's not a lot of like independence that needs, but AI does well. And then here, the code change is what AI is great at, like generating code from an input. So we don't, like with agents themselves and telling the AI what to do if it finds an issue, we already, from what you described about what this memory banking does, like about fixing its own problems without you having to intervene, we can do it.
I mean, it's like a process for using AI in a consistent manner.
Okay. Oh, this we don't have. It's it's very annoying how inconsistent it is. Yeah.
Consistent in the sense that when you interact with the AI, whenever you produce some new knowledge, it associates that into a markdown file.
Okay. Yeah, this we done manually.
And change it if you change you ask another question that requires changing something that you already have. So
this seems like something that would have saved us a bunch of time in building all these agents. Because this is like, we were interacting manually with it. No, don't do it like this, do it like that. And then later, like, okay, now we have to write the agents to tell. So, but we did that manually. So this, I think it's something that could help us writing newer agents.
The only thing that gets closer to this is when I was talking about the decision making, and he asks us, like, what's the decision that you want to make? And you know, all of that knowledge that you produce as you're interacting with the agent ends up being saved in a markdown file in the repository. You can always point back to that. If you see the AI trying to do something, and you can always point back to that knowledge, and you will be like, oh, okay, I shouldn't do this, I shouldn't do what we agreed upon. But that's the closest thing to what you described.
But this seems like a more reliable way of doing that.
Yeah.
You should look into that.
Yeah.
Because sometimes it's like, we tell it to save it and it doesn't. Right? Thank you.
So my only question is, why Quint and not Pascal?
Oh, very, very good question. Okay, so we have that in our FAQ in the website if you want to read, but I'll explain now. I love this question. So Pascal aims to solve the same issue as Quint, which is TLA plus is hard for engineers or developers. It has the same goal, but they took the completely opposite direction. Okay, so they thought like, well, maybe the problem is this like declarative syntax. People don't know functional programming. It's too hard for them to think declarative. They have to think imperatively. So they maintain the same syntax. So Pascal has very like similar syntax to TLA plus, but it's imperative, and they think this will solve the problem. We think the opposite. We think the problem is not that it's declarative. Quint is not imperative at all. We just change the syntax. So they kept syntax, changed the paradigm. We kept paradigm, and changed the syntax.
Sure. This is more logical than functional.
Yeah, but I said functional because of the declarativeness.
Yeah.
thank you very much. That
Thank
was
you.
We're gonna move to the next topic. Just want to thank you guys that are here right now. We're the ones that are doing that for some people
there are already, parties and whatever, but you guys are here from the side, so thank you so much for staying and paying attention. Please, brother, you're the next.
Só um pouquinho, deixa eu largar aqui.
Depois você põe.
Dá outro.
Obrigado. Vai saber?
Caralho. Não, esvaziando.
Você vai no microfone? Vou apertar o botão.
Esperando ele mexer.
Aqui na gola fica bom. Entra.
Hey everyone, I'm Castillo. So I was actually a bit worried about this call because I'm also talking about Daily Plus. I was a bit worried because I didn't have a lot of explanations about Daily Plus, so that they was all that work for me. So I'm very happy about that. I thought this was a formal spectrum development, but it would be for formal spectrum development. It's not really something that we are something that we have a lot of experience running around, but it's something that we're working on. And so what I really like how we have been turning out because we had groups in the beginning and now we're having model training. But what we're doing here is we are moving forward on our sector.
Yeah, that's the thing. It's already in the language actually. Right now, what it just is, it's just a form, but it's very technical. I'm actually going to talk a little bit about that. Because that isn't really included. So essentially, we have like this tool. So Mix is the Elixir build tool.
Just change this one. The battery is run out. Thank you. Sorry.
So Mix is the Elixir build tool. So we just create this command like mix infer, and I can say like infer dynamo client cap IO, and it will show me like all the functions that might perform IO. So the main point here is that like, okay, we generated this from a spec, but we also want to have information in the other direction. We want to be able to like quickly get the most relevant information from the code we generated, so that we can look at like the model and what like the info we extracted from what we generated, and we can say, okay, do the important parts make sense? And the third thing, which I'm not going to go as deep as the other ones, is red flags. So we have like a tool called Sedlex. It's also based on another existing Elixir tool called Credo, which essentially does some of those like old school analysis of like the number of code paths in a specific function or functions that are above a specific size, because those are also usually signs that the AI might have gotten something wrong. The AI might have generated something unnecessary, essentially. And one thing that is really interesting that we do that I couldn't generate an example here is essentially we can extract the model structure and we can compare it with the spec that with the GraphViz spec that we generated in the beginning. So it's like, I think the most important thing is that we start having this bidirectional flow of information where like we can first give the spec to the AI, and then from the code that the AI generated, we can also extract things. So the main thing here, right, is that we usually write a lot of code, and a lot of that is just mechanical in a way. We just know that this needs to work, and like the really interesting parts of code are usually a small part of the code you end up actually writing. So the problem we're trying to solve here and what we're using specs to do is really how do we separate the parts of the code that matter, and we make ourselves able to focus on that part, on those parts, and just let the AI take care of the rest, and we still have a reasonable amount of certainty that what we generated is correct, without having to go into the details. So this is another command we use a lot. Like I showed that graph in the beginning, and like you have the ability to just generate a graph of what is in your project, essentially, and what calls each other and what parts of the project are talking to each other. So we use all of that as like a way to layer our checks so that we can have a reasonable amount of certainty that what our AI generated makes sense, and so we don't break critical systems. So I want to talk a bit about this, but like I said in the beginning, this is very much a work in progress. A lot of these tools are a complete mess. So what we're doing right now is we're cleaning these up and we're improving these because we want to open source them. Specifically talking about xinfer and cap border, we have a lot of implicit info that we can extract from functions just from inspecting their AST, for example, that we're not doing right now. So it's something that we really want to do in the near future. And yeah, right now, like generating tests from specs is something that we are doing, but it's very manual still. So I actually want to talk to you guys later about this, but it's something we want to automate, and we want to support different spec languages as well. And the GraphViz integration as well is very manual. There exists a library to build GraphViz files from Elixir in Elixir, but there is none for parsing and extracting data from GraphViz files. So we want to be able to ask the question, okay, given that we have this module structure, we already have a tool to generate the call graph essentially from the compiler. Now just take these two files, which are very well structured files, and say, okay, do these two look alike? What's the diff here? And not just a simple diff, but actually do like a structured diff of the information in those.
And the other thing is, like, when we're doing our model checking, we're using TLC, which is the simpler, older checker that usually comes with TLA+. There's also a newer checker called Flaps, which essentially the difference between them is that TLC, it essentially converts your model to a SAT problem, and Flaps uses SMT, so that's a lot more efficient. It deals a lot better with very large state spaces. No. No, yeah, exactly. But it converts the spec into an SMT problem and passes that to Z3. Yeah. I might have gotten that one wrong, but like I'm pretty sure that like the approach that Flaps uses have something. It uses like SMT under the like. Yeah, exactly. Yeah. No problem. I'm glad actually. Yeah, and this is the other thing that like Edu mentioned. So Elixir is implementing set theoretic types now. And this is something that I'm really excited about. It already works pretty great. It already helps us identify a lot of errors that like before wouldn't be automatically detected by the type system. And once this is done, I would like to replace the dialyzer integration by the native types. I just have no idea if that is going to be exposed to users, but God, I hope it is. And yeah, so specs are a pretty good tool for iterating. I think that's the first thing I wanted to make sure to like talk about. Like we talk about specs a lot in terms of like proving that things work and things like that. But I think a really underrated use of specs is just like sit down, look at a spec, check a few properties, change some things, see what breaks. That teaches you so much about the system you're building. And I think a big problem, my problem personally with using LLMs for code is that like I can build an entire piece of a system and feel, okay, I've built this thing. It very likely works. I have no idea why it works, and that bothers me. Like one thing I felt a lot like developing with LLMs as well is that, okay, you can ask an LLM to generate the code, and you can read the code, but sometimes like I was talking to Edu about this like a minute ago, going through the entire code that an LLM has generated and actually checking manually that all that works, sometimes you can lose the entire time advantage like from actually asking it to generate. So the big problem I was trying to solve here, and that I am trying to solve, like I said, this is a process that we are working on, is exactly that. How do you get to what matters? How do you separate what matters from what is like just an implementation detail? And one thing I think is really important is this ability to actually ask questions about your code and get an objective answer. You're not like getting the model to tell you what it thinks the code is or to generate something from that. No, you're actually getting something objective. So build those tools. I think like if you're going to be doing any kind of work with LLMs, build those tools. The tooling right now, I don't think it's really there, but I think like you should feel really empowered to just like build your own tools, make things that will extract information from your code and will make you be able to easily figure out like, okay, what's going on here? So like before LLMs, you were talking to your compiler, you were telling it to do things. Now you should be talking with it. And I think like specs can be an important part of that conversation. So just recommended reading here. If like from Gabriela's talk or my talk, you got interested in TLA+, AWS has this really great write-up on how they use it internally, and this inspired a lot of what I'm doing and what I'm trying to do. And the other one that I'm really interested in is Kani, which is a model checker for Rust. And it's really interesting because what they do is they actually take, like, I think it's the MIR. It's one of the intermediate representations that Rust uses. So they take the MIR and they actually generate the model from that. And so that's very interesting, because one of the big problems you have with like model checkers is that if you have a very specific corner case where things might break, your checker might never get to that specific state, depending on how long you have for testing and how much you expand the state space. So using the actual language representation, they are able to like really laser down on things that might be corner case. They are able to use like the control flow graph to guide the model, essentially. So that's really interesting, and it's something I would like to do as well. But yeah, that's it. Thank you.
Really good take on reducing like the space where you can find bugs. I found that very interesting. Question: how you talk a lot about different groups, and wonder how much you apply that already in the HPA, and if is avoiding the bug, is natives go faster. Like how much that improves?
I'm not going to be able to give you a number here. I certainly feel that like, I think we probably are avoiding bugs, but I think the main advantage is that there's a certain kind of disempowerment, I think, that can happen when you start using a lot of AI-generated code. It's like, okay, like I said, okay, this works, but why? And I think the biggest gain is avoiding that. Like, you're giving people tools where like they can feel like they have a handle on what's going on, essentially. That's important to me, and that's important to a lot of people in my team, I think. So I'm not going to be able to like quantify how many bugs we have avoided, because we are building our AI strategy around this, actually. So it's not like I can say, oh, before we were using AI and we had X% more bugs and X% more issues or stuff like that. But I think it's more about like making people really like able to feel like they can come in and they can get a good idea of what is going on, even if most of the code is generated.
Awesome. Any more questions? No? Eduardo, thank you so much, brother.
Última talk.
Vai ter passador aqui, tá?
Vai ativar o espaço, vai em monitors, displays, aí vai ter lá screen.
Você quer clicar? Estender? Eu quero eu vou ter a mesma coisa. Acho que é legal. Deixa eu ver. Agora. Tem como ver todas as imagens.
Wait, your name is not Eduardo? It's not Pedro. Sorry, that is Pedro, guys, not Eduardo. This is Eduardo. Sorry, Pedro. No problem, man. Too many Eduardo.
Boa. Colocar o nome dele. E deixa eu ver se eu tenho acesso às minhas notas. Como vai? Ah, pera, eu não consigo ter acesso às minhas notas e passar os slides ao mesmo tempo. Não, porque tá no VS Code. Ah, mas... Deixa eu ver. Não, agora vai. Aqui foi. Primeiro, boa noite. Sorry, it's going to be in English. I forgot about that. First, my name is Eduardo. I like types in programming languages. That's kind of it. I don't have a degree, so the stuff that I'm saying here is mostly, you know, I just figure out by myself. If it is, you know, if it is wrong at some point, feel free to correct me. Today we're going to be talking about rewriting, sharing, and optimality. Rewriting as in rewriting systems, sharing as in sharing in terms of rewriting systems, and optimality, which is about rewriting systems. This talk is going to be mostly about the lambda, in the context of lambda calculi, so like plural, not just the lambda calculus, but also derivatives. Rewriting is pretty much just a standard technique to describe operation on terms. So it's like operational semantics. You're saying what your program do, and in general we say, okay, the program is what it does. And so in general, rewriting is small step. So that means that we just have a bunch of small steps and we play them again and again and again until we get to something. Often that's called the normal form, but it may be a stuck form or something like that. I'm not talking a lot about semantics though, because I'm mostly interested in the rewriting part. So why should you learn about rewriting systems? It's mostly how languages run. So if you go to check almost any programming language and you ask, okay, what is going to happen on the next step? And even what is the next step, right? People often think that code runs from top to bottom. But if you get any composed expression, like let's say I have 1 + 2 and 3 + 4, this can happen in any order, right? The reason why it can happen in any order is because for this subset of the language, we say that it's cofluent. So there is 2 options. You can run first 1 + 2 or 3 + 4. You can choose. It doesn't matter. At the end, it gets back to the same place. It's also very interesting to reason about performance, because if your language has what we call a reasonable rewriting system, and the reasonable here just means that the cost of the language, of actually running the language, maps to rewriting systems, to the rewriting system. You can just count the number of steps, and that gives you an approximation. Not all rewriting systems are reasonable. For example, the lambda calculus is not. So if you just try to say, okay, my lambda calculus runs 4 or 5 steps, depending on my strategy, that does not say that it's faster, because sometimes doing more betas is better than doing less betas. But mostly importantly, the reason why, what happened? I don't know, what is that? Okay. Mostly the reason why I learned about rewriting systems is to win an argument on the internet, okay? I was saying, okay, this does not make sense, and you know, I needed better tools. So it's also like for I'm gonna call normal languages, which are eager languages, strict languages. So you think JavaScript and whatnot. It mostly doesn't matter that much, because that's actually the easy case. Now, as soon as you go to a language that has either laziness, like Haskell, or it has what we call strong evaluation, which it run code under lambdas. So you have a function, it may run the code even though the function was not called. There is a couple good reasons why that's very good for performance. And it's especially useful for type checkers because of this. This is all the Greek that we're gonna have on this. What this rule is saying is that if M in the context gamma, M has the type B, and in the same context, A is equal to B, then M can have the type A. That makes sense because, well, you said that M has the type B, B is equal to A, then M has that. The problem is running that. How do you check if A is equal to B, right? That may actually be quite slow. In fact, that may take the age of the universe. For theorem provers, like Lean or Rock or Agda, we know that it terminates, but it may be very, very slow. So one of the things that it's very interesting about rewriting systems is that this is the core of that equality. Because the way that we do that equality. So exactly, it's the core of conversion checking. Whenever you want to check if two things are equal, you run both of them, you normalize them, and you say, okay, now that they are static, there is no moving part anymore. Are they the same? And the second part is easy. The running is a bit harder. I'm going to start with a small rewriting system. Rewriting systems are often given by like the language in BNF grammar and a couple equations. Those are equations, even though like they have a direction. So in general, we think about them as going from left to right. You could, in principle, run them in reverse. Because remember, equality, two things are equal if they reduce to the same thing. And 0 plus n is equal to n because 0 plus n reduced to n. Here is simply for like, I'm just giving a small language that has the piano naturals. So it's like 0 and 1 plus n and 0. And also two operations, addition and multiplication. Don't pay too much attention, but that's how addition and multiplication is done on the piano naturals. And you can look at the example. Whenever you see like 5, you should just think that it's suck, 0 at some point, or like. And here I just use the equal sign to say that I'm converting the syntax. But yeah, it just goes step by step by step by step. But you can do the steps in any order, as I mentioned, but not all the paths, and this is how equality is done, sorry. So you can see that 3 plus 4 goes to 7. This is clearly, it should be a 1, and that should, but that's just not right. Look, it was 1 a.m. when I wrote this, so. But imagine that this was two things that go to the same, they should be the same. And let's see. And as I was mentioning, not all reductions have the same length. So here on top, I have one reduction, and you can, because it's 0 times anything, it's always 0. You can go always to 0. Or I can just play the game slowly by going on the other path. Notice that both paths produce 0. But they are not the same whenever you start to think about questions like performance and just how much memory it's going to use and things like that. But you can see that the rewriting system thing actually kind of maps well to an interpreter. Let me try to find. So this case becomes this. This case becomes the first case becomes this. The second case this. The third this, and the fourth this. And this is like the naivest interpreter. This is done in big step. You could do it in small step, but like there is a couple of reasons on why not to do it. Sorry, I lost. But also notice a thing, just going back quickly to the path. The path length, remember that I mentioned that not all systems are reasonable. If you think, like, I can go to the bathroom is there. There is many paths. I could first go there and then there, or I could go directly there. You may say, oh, going directly is faster. That depends. If I start very slowly going to the bathroom, that's going to take a long time. If I just walk normally there and there, it's going to be faster, even though the path is longer. So a good rewriting system, I would say, it accounts for things like the speed that you're going and not only the path. So the path is actually a meta path. It's modeling both variables like speed and the path length. And but most of the talk is not about like arithmetic. You guys know how to do arithmetic. If you ever wanted to implement a calculator by hand or something like that, especially one that works for very large numbers, you shouldn't do this because this is going to be very, very slow. But it does work. I don't know if you can put like any number, any natural number that you think here, and it's going to work, even though it's going to be insanely slow. But sorry. No, go for it.
What's the meaning of speed in terms of what you just presented? Because I understood that your notion of performance was associated with the length of the computation.
Yeah, what would be the speed of the step?
In a good system, that's true. But imagine that I compile this, or I make an interpretation of it in a traditional Turing machine. how many steps is that going to take in that Turing machine? Or even better, what if I compile this to like x86 assembly, right? How much is that going to take on x86 assembly? So whenever I'm talking about performance, I'm talking about actually, how many clock cycles you're going to take. What I'm saying is a good system, by measuring the path length for a reasonable system, that's the proper wording. By measuring the path length, you have an approximation to what the clock is going to be. And in fact, it's amortized to be the same. So if I know it took 1,000 steps, and I know that every step amortized takes like 10 cycles, it's going to be 10,000 cycles. This is true for some systems. In fact, this one is one of them, but not the lambda calculus. So this is mostly a talk about the lambda calculus, because it's the core for like pretty much all the functional programming language work that exists. It's just like, if you want to think about running code without considering performance, the lambda calculus is the tool, without considering performance. As soon as you start considering performance, the lambda calculus stops work. And the reason why it stops work is because the lambda calculus is bad. Like, Alonzo Church was an amazing man, but this is not very good. This is just good. This is traditional. It's Turing complete. It has confluence. It has like all sorts of good properties. We all love it. But beta here is a very big step. Like, what beta is doing is that if you think about it, it's pattern matching on the left. So it's saying it's a function and an argument. And then it's doing a substitution. It's saying, okay, I'm going to get the body of the function, and I'm going to replace the x by the n. This is doing like at least 3 different things here. And in fact, if you split them apart, it becomes 2 or 3. And that syntax just means, as it's written, it means k where x is substituted by n. So this is just, it's enough for you to know what is going to be the end result. But it doesn't tell you how you're going to do each one of those steps. And what's substituted by means it's also like underspecified, but this is not a problem in practice. We have solutions for that. And here is 2 examples of something showing that the beta that you want to do, the reduction that you do first, matters a lot for the length. For example, here if I do the first beta reduction here, it goes directly to the end result. So it's just one reduction, it finishes. If I do this one first and then the left one, it becomes 2 reductions. So not all paths have the same length. And so I can ask more about strategies. There is a bunch of strategies. For the most common ones are call by value, weak call by value more specifically, which is the one that you're going to find in like JavaScript, Python, C. Like for all of those languages, if you just compile them to the lambda calculus, they all become a call by value implementation. And I think it was, for someone who knows the name, it's Eugenio Moggi, I think, is the guy that first gave the interpretation, and it's also where he imported monads to programming. There is also call by name, which is not what Haskell does. Call by name is worse. It is lazy in the sense that it only runs reductions needed. So I'm going to get into what needed means. But it duplicates the reductions often. Go for it.
How would you define formally what
Haskell does call by need. And I'm going to actually get into call by need. So there is a difference. Call by need, you never run it's not that you're never running the same reduction, but there is a definition that they do not duplicate work. Call by name duplicates a lot of work. A nice thing, call by value, naive call by value, which is not a very defined thing, never does a reduction that is not needed. It always, never duplicates a reduction. Call by name never does a reduction that is not needed. And so those, a lot of what we're going to be talking here is about, there is 2 types, 2 main properties, which is, are you doing work that is only needed? And are you doing work that is, and are you duplicating work? A system that never duplicates work and only does the work needed, it's called an optimal system. And by definition, if it has those 2 properties, it has the smallest path length possible. So there is a bunch, if you think that there is a bunch of possible strategies, this system guarantees you that you're going to take the smallest. A property that is interesting before going there is there is two main types of strategies. I mentioned there is a call by value, call by name, and call by need. There is also a weak and a strong version. The weak version, we never run code under a lambda. So if you look here, for example, in the weak version, I only normalize what is under the lambda. This is, again, sorry, it's missing a comma here. I only run the code first on the argument. I don't think this example is right. And then, yeah, so this is oh, no, yeah, it's here. So this is the initial example. If this was a weak strategy, I duplicate this beta because I never run. Notice that this beta here is under a lambda. So this is an argument. I'm passing a function to the function, and that function has some code to run. I could run it before passing the argument. But in a weak strategy, I never do that. I only run the code of the function before. And in fact, if you think about it, in a language like JavaScript, the function is lazy. In fact, it's the main way that you get laziness. It's because the body of the function is only executed when you call the function. This is not true in something like Rock or Lean. You can actually run the code under the function. And that behaves like a JIT. So if you think about it, you're running code inside of the function. You don't know the parameter, so you kind of need to recompile it in some sense. A side note, this is a valid program in the lambda calculus, okay? Notice that that variable x, it's not bound anywhere. This does not happen in traditional programming languages, but it happens at the type level. It happens a lot on theorem provers. And you need to understand that often, if you're running code where all the variables are bound, it's much easier. But if you're running code like that, which you do on the theorem prover, it doesn't work because it just becomes much, much worse. The solution to a specific problem, which is the call by name / call by need problem, is that, and I forgot to introduce, the problem is the lambda calculus cannot mimic Haskell. If you try to do what Haskell is doing in the lambda calculus, it really doesn't work because you need to pretty much do look ahead. You need to delay the stuff and you need to run it because you want to never run the stuff on the argument twice. So you want to avoid duplicating that. That is not possible to describe on the lambda calculus. If you pick the paper and you're going to go, like, there is no naive way of doing it. You need something else. And what you need is not the lambda calculus. You need a lambda calculi. In fact, what I'm going to get here is into a class of lambda calculi called lambda calculi with explicit substitutions. And so they model environments. If you ever implemented an interpreter, often you see environments here and there. They just, X means Y. The way that I know, I go to the environment, I solve it, I reduce, and whatnot. Here is a very standard and kind of modern thesis, I think 2013 by, I think his name is Beniamino Akatoli. It's like if you just go read his work, you're gonna learn so much more. And this is called the substitution calculus. It's the same as before. So we have function, variable, function, and application, but now we have let. That's it. The let behaves like in Rust. It's an expression. And all that it does is it breaks the beta apart. Before we had beta, and now we have beta and substitution. And all that it's doing, and there is one small detail that matters and took like 20 years for us to figure out. All that it's matter is that the beta produces the let, and then the let later may do the substitution. The nice thing about this is that it actually matches how the implementations look. If you write an interpreter, you can see that naively, this is what this describes that, except that there is one point, which is there is an E there on the beginning. That E stands for the environment. It's just a series of let. And that is very important because we can see in this case, this is not a beta reduction. Like, first it happened a beta reduction, but now there is a let between the function and the argument. So this is a distant beta because the environment is moved to the outside, and that's done all in the same step. This is very, very important. If you do not do that, you lose confluence. I don't think you lose confluence in this one, but you lose meta-confluence, which is a different property. So this is the only bit that is like not very nice and whatnot. And you can already see that we can now do what call by need does. This is call by name on the left. And what you can see is that I pass the argument. In Haskell, we never run the argument before jumping to the function. We delay it. It's lazy on the argument. We put the argument here. But notice that when I duplicate the argument, it actually makes 2 copies that have a beta. What Haskell is doing is this. So the difference is that one, before expanding the variable, it does the reductions after expanding the variable. This one, it does the reductions before expanding the variable. And this is the stuff that you cannot do on the lambda calculus, because the lambda calculus really does not have that notion well. And at the end, you can see that that one does 6 steps, this one does 4 steps. And because those systems are very comparable, this is actually just faster. Besides of the memory overhead, there is a bit of memory overhead. Like, this is just better in practice. Let me get my notes again. Nope. Oh, yep. And I'm back to this slide because you can see here the implementation. This is the implementation for this system. And a couple of concepts show up. This part here, we call it a closure, which if it doesn't look like anything like you would expect from a closure, but that's what a closure is. A closure is the environment plus the lambda. And here you can see on the interpreter that when we get to the lambda, we plug the environment back. So we just put them back together. And when it's time to run, we split them. So I split a function with the environment, and now that was not me, bro. I don't think so.
Where's the controller?
Sorry for that, brother.
No, it happens, man.
Oh, your MacBook has a full mic.
Oh, yeah, maybe that's going to work. Nope, it didn't. Oh, maybe it went back.
Yeah.
Now we just need to be able to move this.
I guess someone's just messing with you.
What? I'm not sure if it is the controller or the cable.
It takes a while to connect to Max.
It takes that while?
No, it took like a full minute when I.
Okay.
Sending thoughts and prayers.
Yep.
Stand up section. Jokes.
I don't know, man.
Do you want to try?
I think it's supposed to be connecting now. It's just, yeah, it's just taking forever.
You're saying that you should press the button.
I don't think you should do anything.
Okay.
Sorry.
No problem.
Pressione o botão abaixo. Yeah, we can try that. Sorry, man.
No problem.
This is not the right one.
We have another one here. Maybe this.
Not sure.
I don't think
It's one. I don't think it is. Yep, not this one either.
There should be an input
Yeah,
Oh yeah, it's generate true there.
There? Oh, yeah.
yeah. Let's see if it goes.
Sorry about that.
It's okay, man.
Good work.
No, it didn't. Oh, it did.
Yeah. Woo!
My bad. Okay. This is full screen, I guess. And we're looking here, and blah. Part of the stuff that I was talking is the nice thing about having a good theory, I would say, a good calculus that you can do on paper, is because it actually is realistic. It matches reasonably well to this. This is not the fastest implementation, but it's a good toy implementation. And in fact, it would be enough for, if you iterate over it, it would be enough for a theorem prover. But remember, the goal here is to do optimality, okay? Let is a type of sharing. It's a capture avoiding sharing. There is more types of sharing, but let is not enough. And most of the literature, if you go on explicit substitutions, we get some good stuff. We get strong call by value and we get strong call by need. Those are like really good stuff, but they are not enough to do optimality. If you go to read the work by Delia Kessner on the strong call by need one, she postulates that maybe we need shared environments. That's one way of doing optimality. There is another way of doing optimality. And I just want to show that it's not enough. This, I'm not going to go through the example, but strong call by value runs the first one fast in the minimum path length, while strong call by need does the second one. And no strategy using explicit substitutions only can actually run those two in an optimal setting. Remember, optimal here just means shortest path. That does not mean that it's the fastest path. It just means shortest. None of those can do it. So instead of like, going through, and giving the solution, I just want to explain a bit of terminology. I'm going to talk a lot about the head and the spine after here. The head of a term, so the head of a program, just means the stuff to the left in the application and the stuff to the right of the argument on the left. And the spine is everything else. There is a dispute because depending on your system, so like the body of a lambda, go for it.
Just to make sure I understand, like the head for an application, it is like what you're applying, but for a LED, it's like the body of the LED.
Exactly. For the LED is the return. There is some discussion, and in some systems, the body of a lambda is the head, but some systems is the spine. And that's actually the difference between strong and weak. In a strong system, the head would include the body of the lambda, and in a weak system, it doesn't. So that's a bit of a small difference. But if we go back to, I'm talking about optimality, I'm saying, okay, we can run it in smaller steps and in less steps and whatnot. People have been studying this. Mostly there is a guy called Yves Lafont, and he's known for interaction nets. His work is pretty interesting. I would say interaction nets are not that useful anymore because we have better tech, but it's really interesting to learn about the other strategy that is needed, which is not a let, but it's graph sharing. So here I just give an example of an interpreter that works. This interpreter not only works, it's also relatively fast. And this interpreter is almost as standard, except that it uses mutation. And it runs the body ahead. So whenever it's running, if there is something to run inside of the body of the function, even though maybe the function was not called yet, we're still running the body of the function always. And this is like, I think, the naivest interpreter that you can implement that actually is fast enough for production and that has no bugs. Like this, if you want to make a theorem prover and it's a very bare bones theorem prover, this is enough. Like it runs everything, it pattern matches, it does the lambda. There is no need for let because you're always running the code ahead of time and whatnot. But notice the trick, it's using mutation. Because of the usage of mutation, we get some properties But mostly what I want to convince you is that the usage of mutation here is not just a trick of implementation. It's actually another technique. It's what we call graph sharing. There is environment-based sharing, which is the let one, where you move stuff around. And there is graph-based sharing. Here is an example of a strong call by need. So this is a lazy language. It's not very fast because I think it's because of this. So what happens here is because we are only using graph sharing, and this is the same problem that the interaction nets have, whenever you go to run a function, you don't want to run the argument because you don't know if the argument is going to be used until you run the function. The problem is the argument may reference the environment, but here it's using mutation. So we need to traverse the argument and update all the arguments. And this is also why it's not optimal. Because when you traverse the argument to like solve all the lets, to do all the substitutions, you break the sharing. And that means that at some point you're duplicating a reduction. And this is, again, it's worth it for a tier improver. It's not great. This is much worse, much less practical than the previous one. But I'm going to try to give the general technique here. The general technique is that every node has a label. So if every node has a label, you can think about it as like, originally the program was an AST. But now what we say is that if two nodes have the same label, they are the same node. So now we have some graphs that are like, instead of just being a tree, there is some graphs that are a DAG. There is no cycles here for a couple of good reasons. But like any graph that you can imagine, any DAG that you can imagine, this is modeling. And here you can see an example of what happens with the label. So, sorry, go for it. No, it's just like, this is just syntax for you to imagine that like, on every time that you see a term, it may have a label. Here I hide the labels for the ones that are not duplicated. The label would not appear twice. But you can see that as soon as I do a beta, now there is two nodes with the same label. I just put the brackets. Imagine it's a pair. It's just sugar to make life easier. The thing is, those two nodes are the same node. Even though they're written twice, they're the same. Which means if I do a substitution to the left, I'm also doing one to the right. We call this parallel reduction. This is where the parallel stuff related to optimality comes from. It has nothing to do with parallelism. It has to do like with a point of view. And anyway, the nice thing about this is that this does not need a let. It just has a notion of global variables. And that's kind of it. Lets are local variables. They're capturing a void variables. Labels are global variables. And we all think that global variables are bad, but there is a class of problems that is just so much better when you have them. And this is one of them. But graph sharing is still not enough. What if we use both? This is the stupidest question. There is environment-based sharing, and there is graph-based sharing. What happens when you put both together? I don't know why this does not exist in the literature. When you start to read, about explicit substitutions and whatnot, those two techniques, they diverged in the 90s. And people, they don't talk anymore about that point. I'm not sure if it is one of the cases that it's like a geographical thing, it's the English people against the French again. It's always that. And here is an example of how you could do both. What I'm using here, instead of the label, I'm using the lazy T of the OCaml language. So if you think about this, it's a pointer to a thunk, and that's going to be evaluated. A lot of languages have laziness. Some languages you implement it using functions. And it also has an environment. The environment is not used directly here, but it's going to be used later. And you just do an interpreter. I'm not going to go through it. But what you need to understand is that whenever it's time to execute something, I just update the thunk. So I make another thunk, wrapping it, and I go to the next step. And this is already enough. Like, if you look at this implementation, it's not very complex. And it's like, this is an optimal interpreter. What I want to convince you is that optimality is not about performance. It's a tool to reason. It's about the graph sharing. If you do not have the graph sharing, you cannot do optimality. Why? It's because there is some problems of data structures that you need a different type of sharing. And that actually happens a lot for compilers. First, this is still not great, okay? one of the problems that we have with things like interaction nets is that they lack a tree and a term, a representation that you can write nicely on paper. People used to draw graphs and whatnot, which is nice. But like, did you ever try to draw anything meaningfully big using graphs? You cannot do it by hand. At some point, like if you have 5 lines of code, you cannot translate that into a graph by hand. It becomes like pages of graphs, and it also becomes untrackable. One of the advantages of this perspective is that we get all the traditional tools that we get from the Lambda calculus. And here is, again, I was talking about Lambda calculus with let. We just have a different type of let. We just actually have 2 lets. We have local lets for environment variables, the first one, and we have graph variables, which is the second one. And the main insight here is that lambdas only produce local variables. They do not produce graph variables. And this is where I would say interaction nets gets wrong, and it's where most people get wrong, because if you drop the local let, it's very easy for you to imagine that the function would produce a global let. But then you have all sorts of problems with alpha renaming. You get all sorts of weird things. For this strategy, you don't, because the graph variables are only an implementation tool. They are only there for you to be able to describe, hey, those 2 terms, they are the same. So if I run a reduction in one of them, I get into the other. And one of the interesting things is that there is the naive call by value, which does all the reductions ahead, and it does all the reductions that are not needed. So it does all of them. And there is the call by name, which never does a reduction that is not needed, but duplicates all of the reductions. If you add this in the middle, both of them, you can make them behave like the same. And both of them give you optimality back. Here is the same example. The main insight is that the spine becomes always a meta variable. So remember that I mentioned there is the head and the spine. The head can be, the traditional code, but all the places that the spine happens, like here, you can see that it's a meta variable. And notice that this X is not bound at all. This is just when we expand this hashtag Y, we are literally copying that to here. There is no, renaming and whatnot. This is capturing let. So instead of capture avoiding, it's capturing let. There is a bunch of stuff related to this. The main thing is that, sure, you get optimality. You get to run your code in a different way. It's useful for tier improvers and whatnot. But mostly, it's a unified framework to rewriting. In the same way that the Lambda calculus, you could think about all of those languages, but you couldn't think about the implementation of those languages. As soon as you have this system, all the strategies that you can think, call by value, call by need, the weak call by value, the strong call by value, all of them, you can simply do on top of this. And all of them are kind of natural. You just write the interpreter, and you're gonna look at the code, and you're gonna be like, okay, this is the same. The good thing about that is that you may be like, okay, but programming languages are very standard. They are almost all call by value and whatnot. It's not worth it. This is true for running the code, but there is another case that you run the code, but you don't fully run the code, compilers. So the advantage of this unified framework is that if you're writing a compiler, either for type checking or for optimizations, even for things like speculative inlining, which is a advanced-ish type of optimization, you can just use the same tools. This is not a problem about the Lambda calculus. This is just a problem about data structures. How do I reason about a problem that I want to do the bare minimum of work, I want to delay it as much as possible, and I want to be able to account how long is the work going to take, when is it worth it to delay, when it's worth it to duplicate. By having those tools, which is just this, now you can just start thinking, you can write them down. I have like thousands and thousands of lines of markdown with examples. You also get blazingly fast tier improvers. Like, I'm not joking, you probably get an order of magnitude faster than most tier improvers. Go for it.
No, I just wanted to interrupt you actually. It says it has like 1,000 lines marked down. He's actually minimizing it. He's showing me it, and like most editors can't load his markdown file.
Yeah, that is actually a problem. I'm not sure. I'm not sure if you guys know, but on VS Code, if you try to Control-C, Control-V inside of a big file, it actually shows a loading bar. It's an Easter egg. I don't have it here. It's only on my computer. But when I say blazingly fast tier improvers, I actually say like, if you guys go to check the original kind which was done using interaction nets, it's already so much faster. But with this, you can do better. One of the things that you couldn't do using interaction nets is that there is no compiler for interaction nets. You cannot get that model and produce assembly. This model, it actually works with what we call normalization by evaluation. So you can do a compiler. I didn't do a compiler because it takes too much time, and that was not my goal at the time. But you really do get much faster tier improvers because of that initial goal. We want to check if two things are equal. If we need to run the code, we want to run the code as fast as possible, and that includes things like doing optimizations. But how do you do optimizations while doing type checking? Like, there is some problems involved here, and by doing this, you can like lazily do all the work, accumulate, produce faster code. You have a model for a JIT if you want. You just get faster things. That's kind of it for now. I just wanted to pass over the problems. This is mostly partially a novel result. But yeah, thank you so much.
Yeah.
So, questions? Yeah, of course. Well, wow, that's mind-blowing. Too many questions. Did you publish this? Did you implement this?
Yeah. I have the implementations. I have almost all of them. I'm still working on the proof for optimality. It's very easy to look on paper, but whenever you try to write it on a tier improver, it becomes so much more work than just proving it. Yeah, it kind of.
Is this a tool? Is this a compiler? Is this an interpreter? Is this?
There,
how do you realize this?
there is an interpreter, but for me, it's a markdown file. I'm joking. I'm making my own programming language, and this is a core part of the tools used along the way for doing conversion checking. In fact, I don't run full optimality because it's not worth it for performance reasons, but I do something akin to it. One really nice part of the trick is that everyone has this dream about making a compiler that is just a single pass instead of like, going through the program many times and whatnot. By having this framework and doing compilers in a small step style, which I have another thousands of lines of markdown file about that. I do have a compiler that runs step by step. It makes a rewriting system the whole compiler. And the good thing is that at that point, if you want to run the compiler in parallel, you can. If you want to, whatever is the optimization that you want to do during compile time or during runtime, you can apply the same because the techniques become the same. In my opinion, after you start playing enough, it feels the same as dependent types. After you get dependent types, you're like, okay, so the type level and the term level are the same. Why, it doesn't matter anymore, right? I know how the term level works. I know how the type level works. And I would say that this is similar. After you get it, you're like, okay, my compiler and my runtime is not that different. Again, it's not worth it for, if you're going to generate assembly, not worth it. It's specifically worth it for problems where you're dealing with open code. So like optimizations and conversion checking for interpreters and things like that. I just did. I don't have a degree, bro. I know. Sorry? Of course I can write LaTeX. Come on, man. I just wrote Greek. Yeah, yeah. I need to do it at some point. There is this, and there is another result that I had recently, and that one is the one that I'm working right now, which is about a foundational course. So like the problem of inductive types and whatnot. So I solved a couple of things along the way, and yeah, it's I'm trying, but yeah, it's not that complex. The only thing that I'm gonna say is I'm not sure it's super novel. I think it was folklore in the 90s because there is a note by Yves Lafont. Because if you go to this, if you write this interpreter in Haskell, it becomes the naive interpreter for call by name. I think it is, or it's, no, I think, yeah, if you write this in Haskell, it becomes the naive interpreter for call by value. But because Haskell is lazy, you get optimality out of that. And yeah, it's, Yves Lafont mentioned that in a lazy language, you could do optimality, but he drops the idea and starts working strictly on interaction nets later. I don't know, I checked the literature, I was not able to find, maybe there is something there. But yeah. More questions?
Go on, please. You said you have locals for your role.
I don't have a proof that, like, you know, going step by step, but and I'm gonna say it's trivial because I was actually able to convince people in the past. The main thing that you can notice after you spend, like, you know, if you want it, we can sit and I can show you, is that there is no way that duplication can be happening, and that all the work is happening always on the head. So because there is no duplication and the work is only happening on the head and the head is always needed, there is no way that you may be doing a reduction that is not needed, or you're duplicating a reduction. It literally, you know, you get the proper, and optimality is equivalent to linearity of reductions. Every reduction you do once, and out of those two, you get the linearity of reduction. So,
I work with system solutions back in the university. And one thing that is really hard to get this right. I was formally verified a paper by Elia Kester in 2000. She wrote the paper in 2010.
yeah.
That she was the first one to get a system solution to work right.
Yeah, it's the, isn't that the lambda ES one?
Yes, because one problem that you have, okay, you have explicit substitution, but you are modeling the implicit, let's say, method substitution.
Yeah.
And it's really easy to get it wrong. When I'm wrong, your system is not influenced anymore.
Since the work by, there is the paper, which is called an abstract factorization, something by Akatoli. He introduces the substitution calculus. He shows preservation of strong normalization, confluence, and meta-confluence. And since then, I think Kester adopted the work. And her work on strong call by need, which is later, it's 2013, already uses the approach by Akatoli. I think Akatoli was her student or something like that. So at this point, we actually have the tools. It's kind of weird because until 2012 or 13, it was like all the implementations were, the implementations themselves worked, the theory was completely broken, and Akatoli solved it. And I don't know, maybe the guy publishes a lot, but it didn't get, you know, popular. It didn't become folklore. He's still like a very big researcher if you look at his portfolio. But yeah, since then, we got the strong call by value, which is the first one to have the reasonable property in a strong setting. So like if you count the number of reductions, it does give you performance. And there was some work on optimality, but to be honest, I think people are just legit not interested in optimality that much because it doesn't, we know that it doesn't get you more performance. It's useful specifically in some settings. And the setting that I was interested was not only for conversion checking, but for optimizations. And in that setting, that's where the work happened. But yeah, I have like a dozen interpreters. I have a normalization by evaluation one. And I tried all of them with a couple examples. And yeah, you know, it's. Yeah, no, I understand. That's one of the problems, in my opinion. We know. Yeah. That's why we know some of the examples that I tried the most are reentrance examples, because the ones that traditionally we have, if you go to look at interaction nets, they work very fast until you get to examples that functions have reentrancy, and all of them work. So you know it's not a big sample overall, but it's also like, again, if you look at the code, there is no way that the biggest issue that I was concerned that I actually got it wrong is this. the first time that I sent this entry on the environment was missing, and that was leading to an alpha renaming problem. But yeah, I'm looking to hopefully publish this maybe over the next year, but you know, I also need to work and pay the bills. Thank you so much. Any more questions?
I mean, you can hear the message upstairs.
Yeah, we can talk about
No, I mean like the party is the message.
Oh, okay. So you're gonna talk about free podcast?
Yeah, sure. I was just gonna put the background for you, but I can also talk if you want. There you go.
Also.
So guys, this is just an invitation if you haven't heard yet. I think it's just taking a while. We've been signing this petition. This is not Founder House, but a bunch of dozens of organizations behind it. But we believe Floripa is best because it's great to live, but it should also be 10, like 1 out of 10, right? It should also be 10 for us to build our companies from. So we created this petition to create Floripa Digital Economic Zone, to create a more favorable jurisdiction for us to build our companies from. So we don't need to get out of Brazil to be entrepreneurs. So this is kind of the vibe, to bring Brazilians back so they can live here, but also don't pay crazy taxes, or something like that. So we're still kind of at early days of creating this initiative. We've been talking with the municipal, federal, and state government to kind of create a kind of a sandbox here in the island, to have gringos come all the way here and to build stuff together while we live in paradise. So we have over 2,500 signatures. You guys can check it out. If you want, there's a little flyer here explaining a little bit more. But yeah,
Please sign the petition, guys.
let's make it awesome.
Awesome. Thanks, Paloma. Nice. Well, guys, it was a really intense day today, and that was the idea. I want to thank Eduardo personally for the quality of the people you got here today. It's really nice to see those ideas finally coming together. It's not come over. Where do you find these people?
Twitter.
And yeah. So thank you guys so much. I mean, this is one more event, guys in people are at Founders House. I have a small gift for you guys, which is a cup. But to get the cup, you guys need to take a picture and post something on LinkedIn, on Twitter. So, we got our name around. You have any last messages?
Sure, yeah. Thanks for everyone. It's kind of late. It was a beautiful day to go to the beach. And you guys stayed here listening about pharma verification and photography. Some people came for the barbecue, but I think they already left. But you guys stayed here to the end. So, I'm really grateful because, I don't know, this was just an idea I had at some point. I thought it was going to be cool. I was really insecure if people were actually gonna like my idea and agree to come along. Yeah, you can just do things. So yeah, thanks everyone for coming. Really happy for coming.
Yeah, guys, thank you so much. Let's have a beer, okay? Thank you.
Do you guys want to take a picture before we go up? Is everybody in the front? We need to show people that there's someone that cares about formal verification. Sunday talking about this. You guys are awesome. We really didn't know people were going to show up. We were like, sunny Sunday. This is freaky. But we're proud. And then if you don't want to show in the picture, you can just not show. We also understand you guys are all security people. The way you can skip it is stay behind someone's call.
Yeah.
That's the trick. And you need to show up in the picture. There you go. Perfect.
Yo, Vlad, look. here. Come on, man.
Só gostou?
Na conferência eu vou isso, você pode ver depois, mas então começa a evento.
Muito fácil.
How do we get beer cup? Guys, if you already have posters, go get your cup. Show us the post and then you get a cup.
And also make sure to
Boa. Obrigado.
Dá errado na determinação. Idealmente, você quer que a sua substituição seja verdade. Se for ideal, original é. Então, era outra coisa que era dor de cabeça. E a Adélia faz uma foto fortíssima para comprovar a coordenação.
Uma das palavras para mim insights que eu acho é que ele mostra que o substituto é algo é mais fácil de provar eu faço todos os tempos, mas quase tudo é mais fácil de provar do que ele ia fazer. Na minha opinião, não é bom resultado. Ok, isso a gente acertou em outros detalhes. Só que o problema é que, tipo, quando chega nas versões tem as formulações do sistema legal e o som eu não tenho nenhum vocabulário em português para montar isso.
E a gente já divulga vocês na rede.
Vou saudar você, foi um prazer. Que legal que você conhecia aí, mas muito bom, obrigado por trabalho.
Dá para trabalhar com algumas coisas. Mais de vantagem é essa. A gente trabalha com.
Eu sei. Mas valeu. Você mora aqui?
Não, moro aqui.
Sai para Brasília. Fala aí para você. Mas cara quente. Valeu.
o problema é que, fundamentalmente, esses sons, eles envolvem naturalmente, rodando código bastante social, pode ser aquele, por exemplo, e daí é tipo, nosso CD, nosso. Não, mas se você não tiver, daí fica insano. Porque agora você vai fazer todo o processo, só que exato. O problema inteiro é que em algum momento você se irrita, o Wi-Fi é equivalente assim, e aquilo, é separado, você não precisa fazer o seu modifying forward que tá fazendo bonitinho, tipo, tá mudando ele mesmo em inglês, mas aí você tem que estar atualizando as funções.
Eu não sei, eu acho que isso aí tem que ter algum nível de comunicação simbólica que você já tem.
O problema é que, no geral, se você for pensar sistemas físicos, eles não têm muito para a parte dos chips, e strong system mapeiam para o software mas o optimal, ele mapeia bonitinho para uma nova machine, e daí um dos exemplos interessantes é que eles não têm respostas, que todas as funções elas estão normalizadas e não tem mensagem. Então a gente precisa só fazer uma coisa só que por que você não tem coisa? Quando uma coisa é criada, o código foi atualizado
É bem chato. É possível, eu só gente, eu tenho que ir nessa. Valeu, prazer.
Não vai lá em cima. Não passa a conhecer a calma, né? É bonito lá em cima. Dá um oi pra galera. Guys, let's go upstairs party. Aqui, ó. Onde o pessoal tá indo na parede, dois lacinhos, cara. Pode deixar um mochila aqui que a gente vai. Eu colei um na tarde. Tem caneca, é só mostrar o gosto. O coco é. Eu geralmente não faço. Isso, dá pra sair. Ela é bem
Era feito.
Só que eu fico indo lá, olha pra galera. Mas olha, eu confio em você, pode.
Cada vez que entrava no sala.
Mas não esquece de postar. Não há mais medo disso.
Pensa em uma coisa. Sim, até uma coisa que você vai hoje.
Então, se puder dar uma olhada aqui, deixa eu falar daí.
É fácil de compreender. Você consegue ensinar para qualquer.
Não, eu sei que vou deixar aqui, que daí você vai pegar na saída.
Prazer.
Nossa, eu tô chocada que eu vou fazer tarde. É mais de 100 pessoas. Estou falando, ele tá lá em cima assim, meu Deus. Vamos criar o live? Tem que criar o live. Porque você sai, tá no estresse, fica tudo ouvindo, você mexeu lá.
Só usou esse carro porque eles usavam um exemplo da coisa, né? E aí quando só.
Eu vou saindo daqui a pouco.
Vocês